This conference will now be recorded.
Welcome to the SCADA ICS Hacking and Security course from Hackers Arise. Okay. I get a message here just as I'm starting that there's some, little bit of ins and outs of audio. That's going to happen. Okay. It's going to come in and out. That's part of, working online, unfortunately. So if it's out for any length of time, let me know. But once again, I'm going to welcome you to SCADA ICS Hacking. We have students from around the world, throughout Europe, through all the way to the Philippines, the US, Canada, Mexico. So I want to welcome you all here. I think I'm also going to congratulate you all on your insight to seeing that this is a really critical course, right? This is probably the most important training you will attend in 2022, all right? And if nothing else, the war in between Russia and Ukraine has emphasized that for us, how important it is. We also have a special guest today. Voltage from Team OneFist is going to do part of today's presentation for us, so I want you to welcome Voltage. They've been very effective in attacking the Russians using SCADA ICS. So we'll a little later in today's class, we'll turn things over to Voltage and allow him to talk about what they've been doing here.
This conference will now be recorded.
Okay, so what we're going to be doing is that we're going to start off today, and it's going to be a lot of people aren't familiar with SCADA ICS, and that's part of the reason you're here. And so what we're going to be doing in the next day is to be trying to introduce some of the concepts here and explain why it's so important. We'll probably get into more of the technical aspects tomorrow, but today we're going to focus primarily on trying to get you familiar with SCADA ICS hacking and security. I also should point out that the classes will run about 4 hours, all right? So be prepared for that. Those of you who are in Europe, it probably works out pretty well for you because you guys, it's the end of your day. Those who are in the new world, it's kind of the beginning of your day. But try to block out 4 hours. If you miss part of class, don't worry about it. The videos are going to be available and you can watch them at the end of class. So, and you don't have to announce when you're coming or going. Just go and do that. If you need to go use the bathroom, go use the bathroom. Don't tell us that you have to leave right now to use the bathroom, okay? We will break at least a couple of times, okay? For about 15 minutes to let every bathroom. So 15-minute break, let people, then we'll come back and do some more. Okay, can you hear me? Okay, good. Let's get started then. All right, here's our outline for our course. This is what we'll be doing over the next, 5 days this course is. We're gonna do, first of all, start off with an introduction to SCADA security. We're gonna do what makes SCADA security different, all right? Some major hacks in recent years, and this is where we'll allow Voltage to come in and do his presentation about what they've been doing in Russia, since there's some major hacks going on in Russia right now, all right? Thanks to Team OneFist and other teams who are effectively just raising hell in Russia right now. And we'll talk about SCADA systems and protocols. We'll look at a Modbus simulation lab, some Wireshark Modbus analysis lab. We'll talk about PLCs and ladder logic. We'll do a ladder logic lab. We'll talk about SCADA reconnaissance, how to find these SCADA systems, right, using various tools, right, and how to fingerprint. Modbus systems. If you're not familiar with that term Modbus is a protocol that we'll talk more about in a little while. And today, that is one of the most, it is the most commonly used protocol, but there's about 200 different protocols being used by SCADA systems, but Modbus is the most common. So that's what we're going to be spending most of our time on today and in this class. Then we're going to talk about some hacking and pen testing SCADA systems, talk about protocol hacking and HMI hacking. HMI is human machine interface, okay? And we'll talk about SCADA risk assessment, building a SCADA honeypot. Well, in the end of class, we'll look at more about securing and monitoring and protecting SCADA systems, establishing zones and access control. So this is more from the defensive side, all right? And then SCADA ICS security best practices and SCADA ICS standards and regulations. So that's what we're going to be doing over the next 5 days. Today should be relatively low key in terms of the technical aspects. We'll get it more into the technical aspects in tomorrow's class and do some labs. Today we're going to be doing mostly introductory concepts on SCADA and ICS to get everybody up to speed. You know, some of you may already know this stuff, so bear with us. We've got a lot of new people who aren't familiar with this field, so we'll be doing a lot of introductory material today. Let's talk about what is SCADA ICS. The term SCADA, if you're not familiar with it, is supervisory control and data acquisition, okay? Oftentimes these two terms, SCADA and industrial control systems, are used interchangeably. There's technically a small difference between them. We'll talk about that, okay? So this module is, what is SCADA? Why is SCADA security important? How SCADA systems have evolved. Right? SCADA and ICS are often used interchangeably. ICS is industrial control systems. ICS is a generic term that encompasses many types of control systems found in industrial sectors and critical infrastructure. So primarily what we're going to be doing is looking at industrial systems in general. Whatever term you want to use for them, okay? You want to use SCADA, you want to use SCADA. We're talking about industrial systems, okay? Systems, I've done hacking and security in terms of TCP/IP networks. This is really quite different, okay? Because TCP/IP is used in our traditional systems, but really isn't used in these SCADA ICS systems, at least internally. Externally, when they communicate to the outside world, they use TCP/IP. Internally, they use a large number of different what are called serial protocols, and we'll be talking about those here. What is ICS? Okay, so we have supervisory control and data systems. We just defined that. We have distributed control systems. We have programmable logic controllers. And if you haven't seen this term before, this is important, okay? PLCs are the heart of all of these systems, right? PLCs are small computers that control the industrial process. So they have very simple programs to open valves, close valves, okay? Read a sensor for temperature, pressure, what have you. And these are controlling the entire process in an industrial facility. That's what, if you're on the outside trying to attack, this is what your target is the PLC, the programmable logic controllers. NIST, the National Institute of Standards and Technologies, that's the organization in the US who governs this area, defines SCADA as a subset of ICS. Some examples, and examples are wide-ranging. We could go on slide after slide after slide of examples of ICS. Electrical generation and distribution. So we're talking about the electrical grid. All right. We're talking about both the generation and we're talking about the distribution of these electrical systems. You may be aware that the Ukrainians have had their electricity turned off at least a couple of times, right? And there's a number of attacks that are targeted towards electrical generating systems. Petroleum refining, processing, distribution, chemical processing, mining operations, pharmaceutical, any of the manufacturing facilities. These are all industrial control systems, all right? So SCADA systems are vital components of a nation's critical infrastructure. All right, here's some more examples here. Gas pipelines, water and wastewater systems. One of the things that makes these systems different is that there's a lot of things that make them different, but they often are distributed over very wide, long areas, very wide territories. So for instance, a gas pipeline, you may have remembered that, was it last year in April or May, that there was a ransom attack against the Colonial Pipeline in the US. That pipeline covers a distance of over 1,000 miles, right? So in many cases, these systems geographically can cover, miles, okay, kilometers, thousands of kilometers, thousands of miles. I try to use both measuring systems. Being in the US, very few people use the metric system, except among scientists. I try to use both systems. Okay. Chris says May 6th to May 12th. Thank you, Chris, for updating us on that. That was the Colonial Pipeline. That was where one of the major lines coming from the Louisiana coast area, which is a major oil and gas production area in the US, to the Northeast, where most of the population, or the greatest concentration of the population is at, was shut down for 6 days from a SCADA ICS ransomware attack. And that's something that we have to be aware of. So water and wastewater systems, we've seen a number of attacks against these systems, transportation systems, electrical utilities, refineries and chemical plants, manufacturing operations. Okay. So let's define what a SCADA system is. We know what the acronym stands for, but what can we define it? It's a system that collects data from various collection devices. Okay, so this is key here. It collects data from various collection devices that monitor and or control something and consolidates this as a central server for visualization and historization. Okay, that term historization may be a new term. Basically, think of it as a database, right? So it's gathering all this information and it has to visualize it so somebody can monitor it, right? And also store it in some type of database. They call it a data historian, oftentimes in the diagrams of these systems. So historization. They're used to monitor and remotely control critical industrial processes. Industrial control systems include, okay, so remember we talked about NIST says that SCADA is a subset of ICS. It includes SCADA systems, DCS systems, distributed control systems, programmable logic controllers, PLCs. In SCADA systems, all right, specifically, we have what's called a master terminal unit, okay? It's architecturally unique. We have a human-machine interface, and we'll go through these architectures in a little while. So if you're not familiar with these terms, that's okay. Remote terminal unit, RTU, and then the communications. And oftentimes, most times, within these facilities, communication is over serial connections, okay? Serial connections. That's something that you probably haven't seen before. And it uses a medium very similar to what the old serial printer connections used to use that have been gone for 25 years. One of the things that also makes these systems unique is not only that they use serial connections and serial communication, but they oftentimes are very old, okay? All right, so here's our SCADA components. Let's take a look at each of those, all right? At the heart of our SCADA system, okay, we have PLCs, programmable logic controls, and we'll do more on PLCs later today or tomorrow, all right? This is the heart of the system. This is what's controlling everything. This is making the decisions of what goes on within the industrial system, all right? We have an engineering workstation. We have a human-machine interface. We have a data historian over here, all right? This is a very simple architecture, right? We have a corporate network that's separate, okay, that has been basically segregated from the SCADA network. And this is critical when we start talking about security, right? Is that we want the corporate network to be segregated from the SCADA network. Why? Because if the corporate network gets compromised, we don't want the hacker, okay, the attacker, to be able to be inside of our SCADA network. So it's critical, and we'll talk about more in day 5 about how to properly segregate your corporate network from your SCADA network. So over here we've got the SCADA network, all right? We got a firewall between it and the SCADA network. We have PLCs. We have a sensor or actuator or some other smart device, okay? We might have a protocol I/O translator, so a protocol to translate the input output, okay? And then we have a sensor or actuator. So a sensor is something it's reading data, okay? So it might be, say, a pressure gauge. It might be a temperature gauge. That's a sensor. It's providing information back to the PLC, all right? An actuator is something that actually does something, all right? It actually does some work. And that might be opening a valve, closing a valve, okay? SCADA systems are highly distributed, okay? They're geographically separated assets. So sometimes, like we talked about, they could be over thousands of miles, thousands of kilometers, okay? Their centralized data acquisition and control are critical, such as in oil and gas, electric power grids, railway transportation systems. That makes it particularly challenging to be able to secure these assets, right? Because they're distributed over long range, over many, many miles. Think about a railroad that traverses an entire continent, right? And trying to secure that, or a pipeline. There are pipelines that traverse entire continents. Field devices control local operations. Okay, so think once again about a pipeline, okay? And the pipelines are going to have these field devices set up throughout the pipeline. Those field devices can control local operations, and then they'll feed information back to the central location, so that if I can attack the field devices, I might be able to feed back improper or information that will make the system go awry. All right, so OptFX has got a couple comments here. I'll try to keep up with your comments and questions. OptFX says, I worked at a refinery in Lamont, Illinois during the early 2000s that had all systems interconnected with absolutely laughable security controls, essentially non-existent. Working in one of the world's biggest bombs. Glad I survived it. So this is an important concept here, especially when we start talking about cyber war. These facilities can essentially be both targets, okay, and weapons. So as OptFX points out, that if the security is not properly configured, that an attacker can actually make one of these facilities into a bomb. Okay, so if I can blow up the facility, right, not only is it going to knock out a critical part of the industrial infrastructure, It may kill people. It may destroy the economy. If an attacker can go ahead and knock out a major gas pipeline, um, the economy then gets crippled where that pipeline was supposed to go, like we saw with the Colonial Pipeline. One of the largest industrial accidents in the world took place in Bhopal in India, and this was not a cyber attack, but think of it as a potential of what could take place in a cyber warfare. It was Union Carbide had an industrial facility in India, in Bhopal, India, to make insecticide, right? And this is like the 1980s. If anybody wants to Google it and give me the exact dates, but it's the early 80s, I believe. And that facility leaked insecticide. It ended up killing like hundreds of thousands of people, okay? And the numbers are really not very clear how many people died. Some people say tens of thousands, some people say hundreds of thousands. Sometimes the deaths don't take place immediately, they're long term. People get sick, they die 5 years later. Okay. But once again, that points out the lethality of these facilities if the attacker is effective. Okay. And as OptFX points out, he was working in one of the world's largest bombs, right? The attacker can go in. Sometimes the attackers don't necessarily have to know how the system works. They can just wreak havoc on the system, meaning that they can send inputs, okay, that will make a very finely tuned system not operate properly. So for instance, okay, if a particular valve is meant to open at a certain pressure, if I can change the level, okay, at which that valve is supposed to open or close, the pressure is going to build up too high, it's going to burst the pipe, okay, and you've got all kinds of problems, maybe a major explosion. We saw in the case of one of the once again, not a cyber attack, but a major facility in Texas. Oh, this is probably 20 years ago now, where it was a malfunction of a single valve blew up a multi-billion-dollar refinery in Texas City, Texas, killed 50 people, and destroyed the entire facility, right? One valve, malfunction of a single valve, made the entire facility blow up, right? So that's how delicate these systems are. And so that's why the concern, okay, about these plants in cyber war, well, even not in cyber war, there should be more concern about these facilities because they could be very, very deadly, and they have proven to be very deadly. Okay, distributed control systems, supervisory control of multiple geographic, this is the definition, multiple geographically distributed integrated systems interconnected, responsible for a continuous local process. It's key that most of these facilities require a continuous process. For instance, a refinery, all right, that the refinery cannot shut down. Okay, if it shuts down, it takes quite a while to restart and get going again. So these are continuous process. And one of the things we're going to talk about next is what distinguishes these facilities versus traditional IT systems. And one of the keys is that when you're working in security of these systems, you're protecting the process, okay? You're protecting the process. Usually you're not that concerned about confidentiality, right? So in traditional IT systems, we're really concerned about, having an attacker who's able to access our intellectual property, our credit card numbers, our PII, each of these things. In SCADA systems, that we're protecting them, okay, we're protecting the process, because the process oftentimes cannot be disrupted, right? So that's our key, is we're trying to protect the process. DCSs, used extensively in process-based industry like chemicals and refineries, oil and gas refineries, electrical power generation, automobile production. There's feedback loops to maintain a set policy, and the programmable logic controllers are used in the field as well as in the central facility. Here's a PLC. I'll have some more pictures if you haven't seen them before. PLCs basically run the world. they run the world. Almost every industrial process is run by a PLC, and basically they're very simple, relatively simple, really simple computers, right? They have a chip inside, they have inputs, they have outputs, they have power, and they have some generally simple programming, okay? And what we refer to as ladder logic, okay, is this programming that looks like a ladder, okay, that basically opens, closes, turns on, reads the sensor, closes that valve. That's what it's doing inside of there. And so they control almost all the industrial processes of the world. Microprocessor-based devices used to control industrial processes. They're used extensively in almost all industrial equipment and processes. They regulate process flow, such as an automobile assembly line, a pharmaceutical industry. You know, people don't really think about pharmaceuticals as being an industrial process, right? Pharmaceuticals, you know, there's a lot of research and development, right? It's like they have to find new drugs, what have you. But a bigger part of what's going on is they have to produce the drugs, and that production is an industrial process, and that industrial process is all controlled by these PLCs. Server, that term again, an input-output server, a human-machine interface. The human-machine interface is basically the computer that is used to maintain and control the SCADA system. Okay, I just got a message that the audio went out, but it's back now. Good.
Just for a second.
SCADA server or master terminal unit are also components. We'll look more at these. Other components include RTU, a PLC, and intelligent electronic devices, an IED, sensors, and actuators. Okay, so here's the basic control system components. All right, now this is a simple architecture, okay, of an industrial control system. You can see the corporate network over here, right? We have the SCADA network here, and we have the production network here. Notice that in this particular diagram, they include both the SCADA network and the production network all under the heading of ICS. Earlier, we had talked about SCADA being a subset of ICS. In this particular diagram, okay, you can see that, remember that SCADA stands for supervisory control and data acquisition, right? So that's what's going on here. This is all supervisory control and data acquisition. Over here, we actually have the production network where we have all of the actuators and sensors and the network between these devices. And then the SCADA network is controlling and gathering the information. Here are some operator interfaces. Here's in the pharmaceutical industry we talked about just a minute ago. You'll see that this is the HMI. This is what the HMIs look like. Here's a water system here, a municipal water system. I'm not sure what this one is here, but each one of these is going to have some graphical interface that's going to help the operator to be able to manage and maintain the system. Somebody has to be watching the system to make sure that it's actually functioning properly, or if there's a problem, be able to alert people and do what's necessary. Here's some sensors. Okay, we've got lots of different types of sensors out there. Notice that, oh, I'm gonna back up a little bit here. Notice that many of them, you see they have little antennas on them. So in a widely distributed system, right? So we've got something that maybe an oil refinery that covers, thousands of acres. We might have a pipeline that covers thousands of miles. The various field units need to be able to communicate. And it's not really practical to be able to run Ethernet or serial cable over thousands of miles, right? So what's happening here is that we have some kind of communication that's going on, and we'll talk about those communication protocols later in class, but there is various wireless protocols that are used to communicate. In some cases, they're just Wi-Fi, right? In the simplest case, they're just Wi-Fi. Yeah, Renegade says, imagine blocking the Wi-Fi in there, and that could be an attack if you're local, if you could block the Wi-Fi, if they're communicating. But many of these facilities use different protocols to be able to communicate. But when we looked at in the software-defined radio class, is that you can go ahead and jam signals, right? So even if you can't communicate over those protocols, the attacker can jam those signals. And if you jam those signals, then all kinds of mayhem can take place. Yeah, some of these facilities are so large, there's no way you could run wire between each one of the field units. Here's an actuator. Actuators include valves, pumps, motors, sirens, dampers. All right, so kind of getting our basic terminology down here. Yeah. All right, here's the controllers. These are the PLCs, the intelligent electronic devices, and remote telemetry units. This right here is the Siemens. Siemens is one of the largest manufacturers of PLCs. We'll talk about some of the largest PLC manufacturers, but Siemens is one of the largest. Schneider Electric out of France. Siemens is a German company, if you're not familiar with them. This particular PLC was the one that were being used in the Stuxnet attack. So Stuxnet, we'll talk about some of the major attacks in history. But Stuxnet is that 2010 attack that the US did against the Iranian uranium enrichment facility at Natanz. It's probably people's famous SCADA attack in history. Okay, people would mark it as the beginning of cyber warfare. Okay, and these were the Stuxnet attack attacked the PLCs in that facility and wreaked havoc on that system. Okay, let's see. Daniel says, you need to see the facility around me. Most of them offline, use outdated technology, require human interaction. Okay, well, you want to fill us in, Daniel, where you're at. But the point that Daniel's making, he says, you need to see the facility around me. Most of them are offline and use outdated tech that require human interaction. You're in the Middle East. Okay. So one of the things that we'll see is that many of these facilities, generally in traditional IT, right, to be able to secure systems, we need to be able to update the systems, right? We need to do security patches, right? We need to turn off all the old protocols that we're not using. Right? That's oftentimes almost impossible to do in these SCADA systems. Some of these systems are really, really old, okay? So these systems have been around since the 1970s. Think about the local dam, okay? Think about the local manufacturing facility. Some of them have been around for 40, 50 years, and it's not easy to be able to update. Sometimes you can't update, sometimes you can't patch, okay? And so you have to look at other ways to be able to secure these devices. It's part of the reason why some of these facilities are so vulnerable to being attacked. Okay, Voltage says I have a whole presentation to show on examples as well. Okay, great. Thank you, Voltage. So here's the basic components of a PLC. Really simple, all right? So we have a central processor, right? Of course, it has to have a power supply, right? It has to have some way to program it, right? And usually this is just um, a Ethernet connection, okay? You often have in modern times now, this doesn't apply to something that's 30, 40 years old. We got to keep in mind that some of these facilities are 30, 40, 50 years old, right? But in modern times, we have an Ethernet connection that allows us basically to write our code on a laptop and then go ahead and upload it to the PLC, right? And then we have an input module that takes the inputs from push buttons, contacts, line switches, what have you, and an output module that goes ahead and sends the data out to solenoids, contactors, alarms, motors, etc. Okay, so pretty simple structure here, right? Really, the beauty of the whole system and what makes it really work is the programming, the ladder logic inside of the system, all right? Let's talk about comparing and contrasting the SCADA, DCS, and the PLCs so we can kind of get these terminology firm in our mind. Okay, so in terms of location, SCADA is geographically dispersed. DCS and the PLC are factory centered, okay? Communications, all right, SCADA is long distance and slow speed, all right? DCS and PLC tend to be local area network and high speed. Control, SCADA is supervisory level. And then on DCS, PLC, these are closed feedback loops, right? So why the emphasis? Some of you may recognize this guy right here, okay? From The Simpsons. This is Homer. You remember that Homer works in a nuclear power plant, right? And Homer is not the sharpest. He's not the sharpest tool in the tool chest, but he's running a nuclear power plant. We're not saying anything about the people who run nuclear power plants, but SCADA supports critical infrastructures. Okay, 80 to 90%. Now this is a key element as well. Okay, 80 to 90% of the critical infrastructures are privately owned and operated. So although these facilities have a national security component, right? So if your electrical grid gets knocked out, it's going to be hard to fight a war, okay? If your gas pipeline gets knocked out, right, it's going to be hard to fight a war. If your refinery gets blown up, it's going to really cripple your ability to be able to do anything for that matter. And so these are privately owned facilities, but they are public goods and they have a national security element, right? So okay, we're back. I think we're back. Are we? Okay, good. So these facilities are critical to national survival and prosperity, yet dependent upon industries driven by profit, not security. And that is a major problem. So SCADA, why the emphasis? Okay, many challenges exist when securing SCADA. They're complex systems, right? patching, rebooting, authentication. Okay, these are all more challenging in a SCADA environment, right? You patching, we can, even within a traditional IT environment, patching means we have to take the systems down usually, okay? We have to take them down, reboot them, we have maintenance cycles, right? In these facilities, it's really difficult to patch them, especially if they're really old, because there may not be any patches, right? And even if they are current systems, oftentimes they can only come down once a year. So between the time the patch comes out and the time and the maintenance cycle, it might be 6 months or a year in there where they're still vulnerable to being attacked. Okay, let's see. You got a couple OptFX as federal and military policy somehow fail to recognize this fact. I think they recognize it. They're just not sure what to do about it, right? So they recognize there is a problem here, but nobody's doing anything about it. Now, I will say, and that one of the things, I've been doing this for a while, and I scan the world and test the security of systems. And whatever you want to say about an authoritarian regime like Russia, is that they have, as a being an authoritarian regime, they basically said, hey, you guys, we have to secure our industrial systems. Now, and they've gotten a lot more secure than they were just a few years ago. Okay. I noticed this years ago when I was testing some of the Russian systems, like, wow, these guys have gotten much more secure than they were just a few years ago. Yeah. But they're still not totally secure. But if you test the systems in the West, you find a lot of systems that you can just walk right in. Okay. And it's always amazing to me that they haven't had major security problems. Okay. So OptFX says, as long as it works indeed. That's the mantra. Yep. So nobody does anything until it blows up. that's basically what happens. And then when it blows up, then oh, what how did this happen? Okay. John says, is our aim collectively to offer our services, pen test these facilities on their behalf to earn income? And if so, how we, okay, approach that? Okay. So John's asking a question, is our, this class is designed for both people who are on the defensive and on the offensive side. Okay, there's many different goals here. Some people are going to use what we're doing in class here um, to use it in cyber war. Okay, some people are going to use it for pen testing purposes. Some people are going to use it for coming around from the defensive side and trying to secure these facilities. Okay, so everybody's going to be different. Okay, and in terms of how to approach them, that's really beyond the scope of this class, right? That's here we're looking at how to attack and defend these systems. How to market yourself, that's a whole nother thing. Okay. OptFX says too much bureaucracy in the West. Mr. Daniel says offensive. Yeah. Volta says, I hope that we'll be doing in Russia will help benefit our own countries. Yeah, I think so. I think it will. I think as people see the vulnerability in Russia, and I think Russia is actually more secure than, well, for instance, Poland, okay, right next door, and most of the West. I think it'll initiate, okay, a movement to make these systems more secure. So anyways, getting back to our presentation here, complex systems, patching, rebooting, okay, authentication. Many of these systems have no authentication whatsoever. Okay, you can't reboot them. Maybe once a year you can reboot them. Patching is difficult. Okay, I'm going to go and just kind of catch up with some of the comments here. Paige says, what may be the reasons why works are not being done to secure it? It's too expensive. Yeah, I mean, why are they not securing? Why is anybody not secure their systems, right? Because they're lazy, they don't want to spend the money. We could talk about all kinds of reasons, right? Um, and until something goes wrong, basically tend to ignore security. Bolt just says it's scary how easy it is to get into systems. I would agree with that 100%. It's scary how easy it is to get into these systems. Okay. Control says, if we take aside money and politics, from a technical standpoint, is there a way to implement known techniques, create network process, new loops of pipes with newer components, slowly redirect oil, water, whatever through it, and slowly replace the old technology and security? We'll talk about security. That's what we're going to get into in Thursday and Friday. All right. Will just says risk versus rewards. The companies know it, but with so few actual attacks taking place, it's easier to ignore. Exactly. And each one of these facilities tends to be a little bit different. That's also an important point here. Okay, so that when you're attacking these facilities, if you're attacking these facilities, they're each a little bit different. So the attacks can't be like off-the-shelf attacks. Some can. I mean, there's so much variety among this industry that you have to have an attack that works against a particular protocol, a particular manufacturer, and so it makes it so that these attacks are relatively easy, but they're not for the script kiddie. You need to have a little bit more sophistication, and some of the tools that attackers use won't work in this environment simply because the protocols are different. Okay. This is Mr. Daniel says, I was in Russia last month and they have increased a lot of security around their major facilities. Yes, okay. I got my phone checked just for walking around one of their facilities. Yeah, that's true. They are starting to tighten things up. Okay. OptFX says, I'm in all arenas currently attending a global security program at Hopkins, and the amount of ignorance is shocking. Right? It is. All right. That's why you're here, though. That's why we're all doing this. Okay. Cyber Mayhem says, I'm a complete noob on ICS. Okay. Paige says, we have lots of people here that are giving as much needed additional info on this course. Thank you, guys. Okay. Then Michael O'Brien says, what are you doing in Russia is my question. I'm not sure what you're saying there. What are you doing in Russia, Michael? You want specifics of what we're doing? I think that you're not going to get specifics. Yeah, it's too broad of a question. And there's also some risk of getting into specifics. Okay. Oh, Daniel, you're talking about to Daniel on that one. Okay. What was he doing in Russia? Okay. He was studying master cybersecurity in Russia. Okay. So, anyways, let's keep on going through here. There's a preponderance of legacy hardware. Okay, this is an important element here. Legacy hardware, software, and transmission protocols. So some of these systems are 50 years old, right? And they've got the same software they put in 50 years ago. There's multiple and diverse access points by design, such as radio, wireless, phone, okay? The need to connect to a business network, okay? They need to connect to a business network, right? Otherwise, if they don't connect to a business network, okay, then it becomes more difficult to be able to maintain and control the system. Now, some facilities are offline, okay, are offline. And that would be the most secure way to be able to manage these systems. Because as soon as you put them online, then they are open to attack. So in the case of most prisons, prisons are SCADA systems, right? They are offline. Dams, bridges, major port infrastructure oftentimes are offline. Okay, it's too hard to secure them. So all of the management has to come from internally 24/7. Right? They can't put somebody offline somewhere else managing it and monitoring it. You have to have somebody online. So it gets more expensive that way, but Chris says our water flood plant definitely is more secure. Okay. SCADA systems. Yes, that's industrial SCADA system. Okay. Almost everything that's industrial is a SCADA system. If it's got a PLC in it, it's a SCADA system. And that's basically the whole industrial world. All right. Here's some examples. Okay. Not right now, Chris. Maybe a little later. Okay. Why the emphasis? Okay. The Texas City plant. This is the one that I was referring to. Okay. This was a facility in Texas that blew up and killed 50 people, destroyed. It was a BP, British Petroleum, okay, facility. It wasn't a cyber attack, but all it took is one person, one valve malfunctioning, and the whole facility blew up. Okay. Aurora was a test project that was done in 2007, where a security group was able to um, blow up a generator essentially with just a few lines of code. And that doesn't seem surprising to us now, but in 2007, that was a whole new concept, okay? That you could actually, because everybody was in denial at that point. This is only, what, 14, 15 years ago, right? Everybody was in denial. They're still in denial to some extent today, right? That these facilities can be attacked and raise havoc with very simple attacks, right? So this was a proof of concept where they took a electrical generator, and by just changing a few lines of code, they were able to basically make the thing self-destruct, right? The Northeast blackout in the US, okay, another example, not of a cyber attack, but of simply one component within a distributed control system, an ICS system, that malfunctioned, and we have millions of people without electricity, okay? OptFX says, yep, same thing happened at the sulfur processing plant in Lamont. No cyber attack, but a simple mistake that led to devastating consequences. Exactly. So this is what I'm trying to emphasize here, is that a simple malfunction can create devastating consequences. And it's almost surprising that we haven't had more cyber attacks with devastating consequences. I will say that I know of cyber attacks that have had devastating consequences, but they are not known to the public, okay? Because generally, governments don't want people to know, okay, that these attacks are taking place, okay, and that we're all at risk, okay. So they always like, oh, well, it was just a malfunction by the controller in this particular process, okay. Yeah, it's panic and mass hysteria avoidance. And you talk about the potential policy ramifications of that, whether or not it's a good policy or bad policy, but do know that there are these attacks taking place that you don't know about and nobody knows about, okay? Because the powers that be are concerned about panic and mass hysteria. So, we can all sit here and kind of shrug our shoulders. I never heard of any cyber attacks against these facilities. They are out there. They're being done. They don't get any publicity. Okay. All right. Let's talk a little bit about SCADA evolution. Okay. Let's go ahead and take a 15-minute break here. This is a good time to let people go use the bathroom. I still got some people who are emailing me who, for some reason or another, haven't gotten the code to get in. So I'll take this little break to update them. So let's come back in 15. We'll come back at 25 minutes after the hour, and we'll continue to do our introduction to SCADA, hacking, and security. We'll see you then.
This conference will now be recorded.
Okay, when we left off, we were talking about the evolution of SCADA. So where did this begin? Where did we come from, okay, to get us to this point? For me, this is always an important element of understanding a system, is to understand how it started and how it's evolved. Especially, it's really important in SCADA because many of these legacy systems are still in place today. So if you're protecting or attacking SCADA systems, sometimes you're protecting systems that are 30 and 40 years old, okay? Older than many of you are, right? So that means that you have to be familiar with technology that preceded you, okay? Anyway, so let's start off in the 1960s, all right? So we have integrated circuit, okay? The IC was developed in the 1960s. It led to mini computers capable of computer control of processes. It was confined to a single physical location. It's not connected to any external network. This precedes the internet, right? It's all on a local area network. We had closed loop control and proprietary protocols. There is no TCP/IP, right? So everybody kind of put together their own operating system, their own networking protocols, what have you. Okay. Then in the 60s and 70s, we have central architecture. We have a single powerful computer performing all the functions. This is the old heyday of IBM, when IBM dominated the world of computing with 90% market share. All right. And you'd have a second computer for redundancy. This is an example of a computer room in like the 1970s. Then into the 1980s to the present, we have distributed architecture. We have multiple computers networked together with each performing a specific function. We have local area network improvements, makes them practical and possible. Some of the functions that develop here are remote terminal polling, complex application processing, a data historian for data archiving and trending, and then a graceful degradation. The 90s to the present, okay, we get the client server architecture, we get powerful PCs. Okay, so before the 90s, PCs were not powerful enough to be able to do much other than, a spreadsheet, word processing, what have you. They weren't really large used in business, okay? OptiFX says, I worked in many computer rooms that look just like this. Okay, you're dating yourself there, OptiFX. So they're powerful PCs. We have TCP/IP networking in the 1990s, high-speed internet, Ethernet, commercial real-time operating systems. They're looking more like IT systems. They're scalable and fault tolerant. So this is what's happening. So what these developments are taking place in the IT world, okay, are beginning to get transferred to the SCADA world. Right? That's what's happening here. They're looking more like IT systems, scalable and fault tolerant. Smart software makes redundancy easy. Okay. We get the human machine interface. Okay. These include printouts, a map board, a mimic panel, maybe a video production technology get implemented into SCADA systems. Here's a SCADA. This is a HMI of a particular system. This is the Park Hill Booster and Reservoir overview. All right, so this is what the operator is looking at. Right? The operator is looking at a graphical representation of the system. Right? And so we see a reservoir here, all right, and it's tracking the level, okay, and the PSI of the suction. There's the valve here, and this is the pH present here. It shows us each one of the fire hydrants and the capacity and the pressure. And you can see it's broken up into various zones. We have a pump down here, and looks like there's another reservoir down below. And so this is what the operator is looking at to manage the system. And it also allows them to not only to get a graphical representation of what's happening, and of course, if something goes amiss, to actually be able to manage that situation. Now, if the attacker can get into the HMI, then game over, right? Because this HMI usually can not only monitor but actually control the system. So the software and the system on the HMI becomes really critical to secure. And as an attacker, it's if you can get into the HMI, game over. Okay. See, Chris says, looks similar to the screenshot I was talking about earlier. Okay, good. All right. Optif, it looks very similar to a Scram on Atari. um, Then we have the remote terminal unit in the evolution of SCADA. These are electronic devices located at key measurement and control points. They originally were hardwired. Some of them still are hardwired, okay? Originally hardwired devices with limited capabilities and one proprietary communication protocol. Modern RTUs contain their own microprocessors and can support multiple sophisticated protocols. Modern RTUs are basically PCs, okay, that just simply are connecting to the network. All right. I mean, in the old days, they used to be essentially a dumb terminal that would allow somebody to be able to watch and control the processes. Communications on these systems. All right. Initially used telephone systems and radio transmitters designed for voice. Okay. Those of you who've been in this industry a while will recognize this. Slow, some remote areas had to build their own communication systems. All right. Latest systems are digital network designed to transfer data, such as TCP/IP, wireless, including cellular and satellite. So within these really, really large distributed systems, I mentioned that oftentimes they're so large that they have to use some type of wireless technology. And you'll see that oftentimes they're using cellular, satellite, or Wi-Fi. And we'll talk about that in the physical security of these systems. So to summarize, SCADA systems are based upon computer technology, so they've evolved with the computer technology. New technologies have also been introduced to SCADA systems. There's huge decreases in the proprietary nature. So initially these systems, and some of them still that are out there, are proprietary. They use proprietary technology. Modern systems, okay, use TCP/IP, at least on external communication. That means that they are less expensive, but it also means that they're vulnerable to some of the same attacks and same vectors that we'll see in other systems. It used to be these systems were so different than our traditional IT systems that hackers just ignored them because they didn't know what to do with them. Right? That's not the case anymore. So the good news is that as things have evolved, they've gotten cheaper. You don't have to buy a $10,000 network interface card from the manufacturer. Okay, that would typically what would happen is that when you wanted to go ahead and put a network interface card in, you have to go to the manufacturer. They charge you like $10,000, and now you can buy one for $50, right? So it's gotten much cheaper. It also means that we have better interoperability between vendors, right? So now it's actually possible to buy PLCs from different vendors, okay, and make them communicate with each other. That was not the case before, okay? Cyber Mayhem says, quiz, so which programming language SCADA malware is written in Stuxnet? I guess C-class language. We'll talk about that when we get into various attacks, okay? We're gonna be doing that in just a minute here today, right? So the answer to the question is that there's not a single answer. Okay, we've got multiple attack vectors. It depends upon how you're attacking the system, right? So the bad news is it makes it susceptible to malware, hackers, and cyber attacks now. Okay, we can't go back. Must provide secure designs now and in the future. All right, so we have to move with the evolution of the SCADA systems. We're not going to go backwards, although I will tell you that there have been a number of systems that I've seen and worked with who have chosen to simply go offline. They have decided that the only way they can secure the system is to take it offline. And that raises the costs dramatically. Okay, I will say they're almost always public. They're not private. Okay, they're almost always public entities that have chosen to take them offline simply because they can't secure them properly because they're old and they're too critical to national security. All right. All right, moving on. Let's talk about some of the most significant SCADA hacks in history. Let's get some idea of what's happened in the past. And usually the past is prologue for what's going to happen in the future. So, a lot of people aren't necessarily familiar with, what has happened, all right, and how they went about doing it, and what software that's out there. Very often these attacks are nation state actors, okay? Very often the nation state actors. Why? Because the SCADA systems have a national security component, okay? And two, oftentimes the complexity of these systems makes it where you have to have a team of highly sophisticated attackers, okay, that are capable of developing attacks like Stuxnet. Okay, Stuxnet was very sophisticated, right? And yeah, voltage makes a good case here. So it takes multiple skill sets to understand it. So it's very seldom that you'll see a lone wolf attacker. This takes multiple skill sets, a team to be able to do it. Okay, and voltage has a team that. Okay, we back? Can you hear me? Yeah. Okay. Good. So I was just reading this slide here. So if you didn't hear me, I was just going through this slide. Okay. So we're going to get some perspective on past hacks to get some idea what the future might hold. Okay. Stuxnet. You undoubtedly have heard about Stuxnet. Okay. It's probably the most famous SCADA ICS attack in history, maybe the most famous attack in history, right? This attack focused upon the Siemens PLC controllers used at the Iranian uranium enrichment facility at Natanz. Okay, this is a really good example of a highly sophisticated attack that took years to develop. So if you've heard me on YouTube, one of the things I always emphasize on YouTube is don't believe the things that you see on YouTube. Is that everybody on YouTube is saying, hack such and such computer in 30 seconds or less, or 10 seconds. You can attack any computer in 10 seconds or less, right? That's not accurate. Okay. So in reality, hacking is hard work. Okay. It takes a lot of work. Okay. OptFX says U.S., but let's not forget Israeli involvement. Yes, Israel was probably involved as well. Okay, and Israel obviously has a stake in this. Okay, so yeah, this was a multi-year project. So once again, I simply want to emphasize that if you want to attack, if you're trying to attack sophisticated facilities or well-hardened facility, it's not going to be something you're going to do in 30 seconds or less. You're not going to do it sometimes in 30 days or 30 months, right? So, a lot of people who are new to hacking see YouTube videos and they go, oh yeah, it's really simple. All you got to do is push this button right here. Okay. Or oftentimes I'll get emails that say, I want to attack such and such. Tell me what to do. Okay. And it's not that simple, folks. Okay. Some things are. I mean, some things are simple, but if you're trying to attack a well secured system, it can take years of development, and this is an example of years of development. Okay. So a couple comments are talking about YouTube is like a TV show. Nap says, yeah, the whole YouTube thing isn't doing people any favors. If anything, it may be, it may be deceiving people into the simplicity, okay, of hacking, but at the same time, it reaches a much broader audience. So that's the good news about it, okay, is that it reaches a much broader audience. It gets people interested and involved. So that's a good part of it. One of the things that I do at David Bombal is I always like, okay, you can do this hack, but it might take you weeks to do it. Like this most recent one that I did with David is the femtocell, and it might take days or weeks as a minimum to be able to pull that thing off. As of a day or so. Okay, so that in mind. Okay, that some hacks are more difficult. You just don't push a button and enter inside. Okay. So it's probably the most famous attack in history. Stuxnet, built by the US NSA and intended to slow the uranium nuclear program, was released in 2009 in the Middle East. Now, what's interesting about this is that they didn't actually send the attack to the facility. The facility was offline, okay? The facility is offline. So what they did is they basically released the malware throughout the Middle East. Okay, so it's kind of like random to hundreds of thousands of computers, with the hope that eventually somebody would get infected and bring it into the facility. So this is kind of this is this is it's it's a kind of a shotgun approach, okay, to be able to just infect maybe millions of computers with the idea that somebody's thumb drive will get infected and they'll bring it into the facility. Okay. Chris says, how did it exploit those? It didn't exploit them. Basically, it was like a worm and it just spread across networks. Okay. So they started it out and it just kept on spreading and spreading and spreading from one computer. And it didn't do anything to those computers. It just used those computers as a vector for spreading. Okay. It is kind of insane, but that's what they did. Okay. And so people in our industry were detecting it and going, there's this malware here, but we have no idea what it does. It doesn't seem to do anything to my computer. Okay. And it's spreading across the world, but it doesn't do anything to my computer. It doesn't do anything that uh, the behavior of the computer hasn't changed. It doesn't seem to infect anything. It is infecting it, but it's not doing anything malicious to my computer because it was targeted to just one system in the world, okay? And it was simply using the other computers as a way to spread, okay? So that's kind of a very ambitious and shotgun approach, okay? Cyber Mayhem says also chained, yeah, with multiple zero-day exploits. It has 3 zero-day exploits we'll get to, okay? It used 3 0 days. Okay, Chris asks an important question here. It says, do we know how it reached its destination? The answer to that is no, but we speculate that what happened is that somebody brought a thumb drive into, okay, the facility that was infected. All right, now, was that person an agent? Okay, they may have been an agent to, being paid by U.S. or Israel. Say, okay, bring in a thumb drive, or it may have been inadvertent. We don't know that, but it probably came in on a thumb drive because this was an offline facility. It's air gapped, okay, as we say. It was not connected to the internet, so somebody had to actually physically bring it into the facility, okay? Cyber Mayhem says USB drop attack or what? Well, I mean, think of it this way, is that if everybody in the world, okay's computer is infected, if whoever is going into that facility and anybody who brings in uh, a thumb drive, it's going to have the malware on it, okay? So it could have been an IT contractor, it could have been electrical, it could have been an agent who was paid. Okay. Okay. So we don't really know the how it got in, but there was people coming and going, and it probably came in on a thumb drive. And who it actually came in, we don't know. If it may have come out that they were hoping that it would just inadvertently make its way in there. And when it didn't, after years, then they started targeting people or paying people to bring it in. We don't know exactly, but so it used 30 days of Microsoft Windows operating system to enter the system and then overwrote the ladder logic. Okay, a ladder logic is the logic inside the PLC. So what happened is the NSA tracked exactly what PLCs Iran was purchasing, okay, from Siemens for this facility. So they were working on this for years. They were watching what Iran was doing and then tracking what they were purchasing so that they could develop this. And they developed their own ladder logic, okay, of the PLCs, of the uranium centrifuges, so they could not precisely enrich the uranium at the proper concentration. So this facility did not blow up. Okay, what it did is it did not enrich the uranium at the proper concentration. This was kind of a interesting approach in that if they had blown it up, then they would know something was wrong. The Iranians would have known. But what happened is for years they would take the uranium out of the centrifuges and it wasn't properly enriched. So it took them years to figure out that they had been hacked, right? It's like, why isn't this system working the way it is? Okay, it says that the uranium is. When we test it, it isn't. What's wrong with the system, right? So sometimes, these are the most effective attacks, are the ones that are this subtle that the victim doesn't even know they've been attacked, okay? Still one of the most sophisticated SCADA ICS attacks to this day, and a model of just how targeted and malignant SCADA ICS attacks can be, okay? I have a tutorial on Hackers Arise on a detailed analysis of it, okay? Recently, this is a more recent attack. The Triton X malware was first identified in December of 2017 on the industrial control system of a Saudi petrochemical facility, okay? What makes this malware stand out from this group is that it's specifically designed to kill people, okay? So generally the attacks against SCADA ICS have been to make the facility malfunction. All right. In this case, it actually attacks the safety systems, okay, of these facilities. This malware infects the safety control systems built by Schneider Electric. Schneider Electric is one of the major players. Schneider Electric is the company who invented Modbus, actually a predecessor that they purchased. A company called Modicon that Schneider Electric purchased. So Schneider Electric pretty much, they don't own Modbus, but they are the major manufacturer. They have a system that they call the SIS system that people can purchase that is meant to be like a stopgap safety system. If all things fail, it'll shut the system down. So this malware basically disables, okay, this these safety measures. So it's designed to make the system blow up, right, and kill people. Probably is Russian. Although attribution is always a tricky exercise, and I would agree with that, okay? Attribution is really hard to figure out where an attack is coming from. But there are things that we can do to kind of narrow it down. FireEye, who's one of the leading firms in the US, that's a name that you should know, okay? FireEye reported that the malware most likely came from the Central Scientific Research Institute of Chemistry and Mechanics, a research entity in Russia. This malware is most noteworthy as it manifests the danger of SCADA ICS attacks in a cyber war scenario that could lead to loss of millions of lives. Black Energy is an attack that was done against the Ukrainians, okay, in 2014. Black Energy was a piece of malware that had been repurposed. Right? So it had been bouncing around the world for a few years. It was mostly used initially, Black Energy 1 was used as a DOS attack tool. And this is a good example of where people take malware, okay, and everybody does this, whether you're being cybercrime or you're being the NSA or CIA or whoever, okay? People take existing malware. Why reinvent the wheel, right? You take existing malware and you repurpose it, you redesign it, you re-engineer it. This is an example of a piece of malware that was re-engineered. Black Energy 3 was malware that was repurposed to attack the electrical grid of Ukraine in 2014. Originally developed as a DDoS tool, Black Energy was repurposed to enable the attacker to access systems with an electrical utility in Ukraine. It was a Microsoft Office macro malware that used a vulnerability, CVE 2014-4114 against Microsoft Office 2013 in the OLE packager DLL. The same vulnerability was enumerated as MS14060. It's actually in Metasploit now, so you can go ahead and do it yourself. And the way it got into the system was through a bit of social engineering. So what happened is that the Russians, this is the Russians, of course, right? The Russians used social engineering of basically sending an email from what appeared to be another government email, okay, to somebody inside of the corporate network at the electrical facility. They opened up had an attachment of Word document. So they said, okay, this is somebody important, somebody I know, somebody I trust. I'll open up the document. The document infected their computer, and then they used the access to that computer to take over the entire electrical generation system. Okay, so even the Russians, everybody uses social engineering. Okay, a lot of people, think, oh, well, I don't want to do social engineering. Um, it's been around for a while, it's still being used. All right. The Russians, when they're trying to attack me, and Voltage can speak to this as well, maybe, okay, is that I get attacks from the Russians almost every day, sending me, every day, exactly, every day, sending me documents and what have you, and purporting to be from a student, from a colleague, what have you, always trying to get me to click on something. And so if you send me things as a student, I'm cautious because I get these from the Russians every day, right? They're always trying to send me something, and they'll always say, "Oh, I want to help you with Ukraine," and they'll send me some document that has, um, Yeah. Bolton says, yep, it teaches one to never click on a link without knowing it first, because if you do, you're done. All right. And if I do and I click on something that's malicious, I'm done. All right. And of course, it could put everybody else at risk as well. So I'm very, very cautious, and I almost never will open up a document unless I'm absolutely sure that it's friendly. Okay. And that's very seldom. Okay. So if you send me a picture of your dog and you want me to look at your dog, it's probably I'm not going to look at it. Put it up on Twitter, right? See, Cyber Mayhem says, let's see, it says Russian persistence is like Thanos. Okay. Is there a way to check if a link is malicious? Yeah, you can, but who wants to do that on everything that's coming your way? Right? You can't. I mean, I don't want to be able. I don't want to be doing that all the time. But in this case, this link actually, um, it actually warned the user that there was going to be a macro running. You know how when you get something that has a macro, Microsoft will warn you. But because they thought it was from somebody they knew and trusted, they just ignored the warning. Okay. Voltage says done equals killed. Yeah, if they find you, they're going to kill you. Exactly. That's why I have to be very careful, right? A guy got thrown out the window in DC by the GRU recently, so attacking is real danger. Always be careful. We're not talking about fun and games here, guys. Okay, this is real life. This is life and death. Okay, you got to be careful. Okay. Knapp says, "What is GRU?" GRU is the military intelligence. Yeah, it's the equivalent of like the CIA in the United States. Okay. So yeah, people die. Okay. So here was the warning that we got. Okay, the Ukrainians got on that particular document. Okay. So they did get the security warning, but they clicked on it anyways because it appeared to come from a government official. All right. This attack was eventually used to compromise the human-machine interface and then control the breakers that control the electrical grid. The attackers then selectively blacked out major portions of Ukraine, major portions of Kyiv, actually, to be more specific, during the Russian attack in eastern Ukraine. It's more on Black Energy. You can read my article on Hackers Rise. So this is this was used actually in 2014. In 2015, they used Crash Override, another attack against the electrical grid in Ukraine. So when we're thinking about this. So this is not new between Ukraine and Russia. So Voltage says we got the Kremlin to click a link last week and got the real IP they were at, but the security was too strong for the malware to talk back. Okay. Shamoon, okay, is another attack. Okay, it was designed to steal and wipe out data at the world's largest energy company, Saudi Aramco. This attack was in 2012, overwrote the data on the computer systems with an image of a burning US flag. Okay. Unlike other SCADA ICS systems that targeted the industrial operations, Shamoon targeted the information on the facility's computers. Okay. This is unusual, okay, as most SCADA ICS attacks target the industrial operations and PLCs within the system. Okay. So what it was doing is they were stealing the proprietary information on the system. It makes it more similar to our traditional IT attacks. Can you hear me? Okay, good. Shamoon attempted to spread from the corporate network. Remember that we're talking about here, between the segmentation, between the corporate network and the SCADA network. Right? So oftentimes, successful attacks against SCADA systems start in the corporate network. That's usually the easiest way to get in, is you attack the user in the corporate network, okay, take over their computer, like we showed you Black Energy 3, right? That was inside the corporate network, and then move from the corporate network into the SCADA network. That's why segmentation becomes so key, okay, for security. So if you're working in security, right, You want to make sure that there's as few interfaces as possible and that those interfaces are tracked and managed properly. Shamoon attempted to spread from the corporate network where the data resided to the SCADA network, but due to proper network segmentation and isolation, best practices, which we'll deal with on Thursday, to test to see if they could access, and there's little or no damage. Okay. Nick says, never going to run around and desert you. I'm not sure what that means. There's a lot of attacks. Rick rolling the audio outages. Okay. There's very often very careless connectivity, as OptFX says. There's very often careless connectivity between the corporate networks and the most critical networks such as SCADA ICs. Yes, and that's one of the keys, okay, to protecting these systems, okay, because the corporate network, we've got a lot of systems and a lot of people, and if the attacker can compromise one of those systems and it's connected to the SCADA network, game over, right? So that's why that isolation, that segmentation is so critical, okay? Yeah, so, all right. CC enumerating OTW live, huh? Yep, owned. All right, so I've done this quite a bit actually. So I mean, this is they're talking about this one right here, but this New York dam. I've done this, and so there's probably somebody in Russia or Iran or other places, Poland, what have you, who said, "Oh yeah, we had this attack against this facility. It appears it was just a test." Well, in some cases that was me. All right. Um, so these things are going on all the time. In some cases, it's me. Sometimes it's a nation-state actor. Okay. The attackers access the SCADA controls through the internet connection via cellular modem. Luckily, the system was in maintenance mode at the time, so no control features were accessible. This attack highlights the vulnerability of internet-connected SCADA systems and their vulnerability. Many of these facilities, dams, locks, water systems, have chosen to go offline rather than be online and bear this risk of attack. Yeah. Many of them have gone offline, especially if they're government owned. Okay, at least what I'm most familiar with is in the US. Okay, if they're government owned facilities, a lot of them have chosen to go offline. Okay, I've worked with a number of these guys and they said there's no way that we can secure a 40-year-old dam, right? And most of the dams are older, right? Especially, in the U.S. The U.S. is not building new dams. The dams are old. Many of them date back, 100 years, right, or more. And so there's no way that we can secure this, okay? And so we're just going to take it offline. Okay. Voltage says in Russia they're all oligarch owned. They used to be, right? They now are all oligarch owned. They used to be owned by the Russian government. Okay, so the way that it's important to understand, a lot of people don't understand the history of Russia, but Russia was this great communist state. Okay, since 1917, right? And they disintegrated in 1991. All right, that's why Ukraine is not part of the Soviet Union anymore. That's why we don't have the Berlin Wall anymore. Okay, Kazakhstan became a new state. Lithuania, Estonia. Um, these were part of the Soviet Empire, and they all left. Okay, and Putin is trying to restore the Soviet Empire. He's trying to take those countries like Ukraine, who used to be part of the Soviet Empire, and make them once again part of the Soviet Empire. that's what this war is about, okay? Is to be able to take these countries and bring them back in under Russian control, all right? So when they did this in the 90s, all of the industry in Russia was owned by the state. Right? All the oil and gas, the mining operations, they're all owned by the Russian state. So in the 90s, the Russian state gave away essentially these facilities, the mining operations, the oil and gas, to the people who were their cronies, their friends, and made them billionaires. This is what the oligarch class is in Russia. Okay, they are not business people. Okay, in the classic sense that we have in the West, they are people who have stolen the assets from Russia, from the Russian people. All right, and are making themselves very rich of it. So, like in the early part of the war, we were going after the yachts and other facilities of the oligarchs, and people say, well, they're innocent in this. No, they're not. They're part of the problem. Okay, the oligarchs have stolen the riches of the Russian people. Okay, they're not innocents. They are part of the problem. So that's my my historical lesson on what's happened in Russia. Okay, and it's important to know that these guys who they are portrayed as billionaire business people, they're basically are thieves. Okay. Many of these facilities, dams, locks, and water systems have chosen to go offline rather than be online and bear the risk of attack. Okay. Optifix, this really differentiate from the U.S. Well, we could argue about that. Is this really differentiated from the U.S.? Um, that's an interesting question, and maybe one that we can have offline at another time. But most people in the West, being the U.S. and Western Europe, will go, well, they invested their own money and they built a company, and they're entitled to, the riches that they've built from this company. Whereas, in Russia, they were basically given these facilities. You might, yeah, they got it. In some cases, they got it from daddy, right? In any case, this is a whole different, political economic issue and argument that we could have offline. But it's important to know. Yeah, it's not a class on politics. It's important to note, though, that the oligarchs, are not legitimate businessmen. Okay, that's what makes them a target for in this war. All right. Okay, moving on. Okay, many SCADA ICS attacks go unreported in most countries, including the US. There's no legal mandate to report these attacks, despite their national security implications. So in the US, in many parts of the West, you have to report an attack if you have personally identifiable information or credit cards, okay, are compromised. You legally mandated to report it, all right? That's not the case for SCADA attacks. That's why so many SCADA attacks go unreported. That's why we don't know about many of these attacks, because they don't get reported. All right. One of these such attacks is known as Kamuri, to protect the identity of the company. Okay. It was reported by Verizon Security in 2016 and involved an attack upon a water company. Okay. Voltage says, in Russia, you will never see news of a SCADA attack unless it makes a big fire. The outcome is too large to be hidden. And then they'll always say it was a system malfunction or something like that, and not a SCADA attack, right? They'll never admit, yeah, hot weather was the cause, or smoking in the wrong location. They'll never admit that they got attacked. So that's why I post on Twitter very often, that these are mysterious explosions in Russia, okay? Because that's the way they're depicted in Russian press. Okay. control application against the water treatment, dangerous microbial growth, and not so much to kill the humans drinking it, right? So all of our water systems are once again finely tuned facilities, right? They're finely tuned facilities where they have to add just the right amount of chemicals to kill off any bacteria that'll make us sick. But if you put too much, okay, in there, it'll kill the human beings as well, right? So what happened in Kamuri is that they had control of how much chemicals were going into the water, and it could have been very, very deadly. Okay. Although little damage was done due to the vigilance of the operators, if the attackers had better knowledge of the SCADA and ICS system, and that's really key here because to be successful in these attacks, you have to understand the system, right? And as these systems are, there's lots of variety in these systems. There's lots and lots of variety. So you just can't take an off-the-shelf attack, okay, and use it against any system. You have to understand the system first, all right? And we'll talk about that in the reconnaissance phase and enumeration. You have to understand how the system works before you can effectively attack it. So these guys had better knowledge. Many lives in the community could have been lost and the economy disrupted. Crash override, it goes by two different names. IEC 61820, these are the communication protocols used in electricity distribution industry. All right, so it's specifically designed for that industry. Can you hear me? Yeah, okay, good. So crash override has been used in Ukraine and has been attempted in other places as well. It was actually used successfully in Ukraine in 2015, I believe, right? The modules of crash override in Destroyer are designed to open circuit breakers on the remote terminal units and keep them open by running an infinite loop procedure that keeps even the manual operators on site, okay, from closing them. This attack results in the de-energization of the substations and forces the operators to switch to manual operations to restart the power. Crash override in Destroyer and its variants could be a very destructive attack in a cyber war scenario, potentially knocking out power to large swaths of the economy. In 2014, a German steel mill was attacked with malware that first provided the attackers with access to the business network and eventually the SCADA ICS network. Once again, the attacker comes into the business network, right? That's usually the easiest way to get into the SCADA network. Now, I'm not saying that you can't get into it, and I've got into many SCADA networks by going directly into the SCADA network. But if the business network is connected to the SCADA network, that's where you're likely going to have problems, and that's where segmentation becomes critical. Here's another example of where they came into the business network. If I'm an attacker, I'm going to find the easiest way in, right? The easiest way in, if your system isn't segregated, is to attack the individual systems in the business network and then move from there into the SCADA network, okay? We only know of this attack because it was included anonymously in a German government security report without identifying the company or the facility. This once again underscores that many SCADA ICS attacks are unreported and unknown to the public, okay? The attackers were able to access the industrial control systems and cause multiple failures among these systems. The attackers had an intimate knowledge of the steel mill operation, so here's a case where they knew how the systems worked, right? And the industrial control systems that managed it, the steel mill narrowly skirted disaster. Yeah, Volcher says this is the hard part, and I would agree with you. This is the hard part, is understanding how the system works to be able to attack it effectively. Now, it's also possible, remember we were talking about that these are finely tuned, choreographed operations, right? So in some cases, by just sending random input into the systems, if you can get access to the system and just throw randomness into the PLCs, you might be able to create havoc within the system. So it's important, obviously, I think it's obvious that people on the outside shouldn't be able to send inputs into the SCADA network. Yet you can do this. It does happen. All right. Chris says, would you ever make a book on SCADA ICS? It's under consideration. Okay, maybe in the future. So I got enough things on my plate right now. So, but I definitely, I would like to make a book on SCADA ICS. So, Volta says, like the dog that catches the squirrel and then does not know what to do with it, getting is only 1/3 of the work. Okay. Unlike this is Night Dragon, another one. Unlike other SCADA ICS attacks, the Night Dragon malware was a series of attacks that gathered information from oil, energy, and petrochemical industry facilities. These are often referred to as tactics, techniques, and procedures attack. This malware gathered information from the industry such as financial documents, operational procedures, and bidding. Okay. OptFX as well. Once you've placed something persistent in the network, let the games begin. Yeah, if you can get inside the network and get persistence, then game over. This attack in 2010 highlighted how unprepared the industry was to attack. So, like I said, in 2007, when this proof of concept of attacking the electrical generator came out, even after the proof of concept, the industry still said, no, that can't happen. We're in denial, and some still are in denial, but the impact of these attacks is beginning to sink in. Okay. Just a few years ago, people were in total denial about the importance of security in this industry. And that's why, in some cases, you can walk into these facilities using default passwords. Okay. So this could be a rather unsophisticated attack, but could have caused significant damage if the attackers had targeted the HMI or other industrial control systems. Of course, bringing us up to the present, okay, or close to the present, this is actually a year ago, okay, is on April 29th of 2021, attackers took down one of the largest fuel pipelines in the US. The hackers gained entry through the VPN with a compromised password, right? A week later, on May 7th, the control employee saw a ransom note at 5 a.m. By 6:10, the entire pipeline was shut down. Created shortages and price spikes in the U.S. East Coast. Colonial paid a $4.4 million ransom in Bitcoin, and reportedly, the FBI was able to recover portion of that ransom. So that's, oftentimes people think that you can't track Bitcoin or the other cryptocurrencies, but the truth is that you can. Okay, it's just hard. And we've seen a number, if you have the resources. Now, for most companies who don't have the resources, tracking the Bitcoin is going to be fairly expensive. In this case, the US saw it as a national security issue, so they put the FBI on it, and the FBI has special teams that were able to track the Bitcoin and recover it, all right, before it was laundered, okay? OptFX says on the defensive side, you're most certainly at a significant disadvantage by far, yeah. So, oh, I included you in here, Voltage, okay? Team One Fist, a group of volunteer cyber warriors fighting to save Ukraine, okay? Was able to destroy a natural gas system at Russian oil hub on August 23rd, okay, 2022. So this is Voltage's Twitter account, okay, and took a month of planning. So I'm going to open it up to you, Voltage, okay, and you can now tell us more about what you guys have done, and you know, be
Sure.
keep in mind, just keep in mind not to reveal too much information because these videos will make their way into other people's hands. That it may compromise some of the things that you're doing. So maybe just talk about the past and not talk about the future. All right.
Okay. I did. So
Okay.
should I not show the presentation for now?
You know what I can do is I can turn over, if you have the presentation, you
I
can
do.
either send it to me via email,
You have it.
or I have it in email.
Yes,
Okay.
you do.
All right. Let me
I
go.
sent you the PDF
Hang on a
and
second.
yep, and the actual PowerPoint so you can use the slides later for things.
Okay. Oh yeah, here it is. I've been teaching, so I didn't check my email. So let me open up your PowerPoints. Hopefully there's nothing malicious in it.
Nope.
All right, I'm just teasing
No, it's a very good point. I sent you a
you.
PowerPoint.
Let me download it, and
So we started. I'll just give a brief.
let me get it
Um,
up on the screen first, okay? And then
sure.
we'll there it is. Okay.
Okay. So made this presentation for today to talk about our experience in Russia, um, and what we've gone through. Low and high level SCADA attack. You can move forward.
Okay.
Next slide.
All right, here we go.
So low level attack, what we call a low level SCADA attack, is attacking the PLCs directly, as OTW has discussed, where you can find PLCs on the open internet in Russia that are not protected in a backnet. This is true. It's not good. It's not standard practice, but it exists a lot. And these kinds of attacks typically they're network attacks where you can't program the PLC to do exactly what you want because the controller is sitting somewhere else talking to the PLC to do that, but you can break the network. You can disconnect the Wi-Fi, you can break the WAN, and you can knock it offline. And this using this method of attack, next slide, we
Yeah.
actually created a fire at a power plant and knocked another one out simply by knocking one of these PLCs off the line over an electrified train bridge. When the electrified train bridge needed to shut off, it was obviously stuck on, and
I noticed
created.
they're using OpenWRT
It's
here.
my favorite. It's my
Are you
favorite.
are you finding this a lot in Russia?
It's everywhere.
It's
Imagine
everywhere.
being in the early 2000s. Yes, most systems are 2015 to 2018,
Hmm.
and you'll find a lot. Next slide. You'll
Okay.
find a lot of this out there. This is another example. Now, when you're doing low-level SCADA attack, as we've done, oftentimes these will have multiple networks attached to them. These teleoffice ones, there were 120 of them that we bricked, and these were special because they were connected by a phone line. Each has a dedicated cell phone connection, and that's how they connect to the internet, meaning they were too far away from a Wi-Fi network or a wired network. So probably like wind turbines or rail monitoring systems or track switching, stuff that's too far from the city. So we found a bunch of these, and they, as OTW described, the actual PLC connected to this device, um, and it does SCADA as well, is on a tiny little backnet of its own, and it's just one PLC that connects to each one and does its thing. And then there's WAN and internet. These teleoffices were pretty robust. Next slide. Yeah. So I won't stay on each slide too long because there's
We
40.
lost we lost you there for a moment.
Oh, next slide.
Okay.
You didn't miss anything. So just a real quick diagram of how these typical PLCs on their own works. In this case, you've got the on-cell devices, which will talk to an industrial controller of its own, and then these little communication PLCs talk back to the server, which does all of the actual SCADA stuff. So if you can intercept and log into one of these network PLCs, you can break the connection to the PLC, which is random. You don't know if it's going to be good or bad, if it's going to cause damage or not. And that's kind of the downside of it.
But the
Next slide.
thing is that what's really important here is that usually these systems there has to be communication between them, or the system won't work, okay,
Correct.
well. And if it
Correct.
doesn't work well, you don't know what the outcome is going to be. It could be an explosion, or it could just be that one piece isn't functioning. But this is, I think, an underutilized attack against these systems, because if, like, thinking about the example of a refinery, if there's not communication across multiple parts of the system is in danger of
Oh yeah.
some type of unexpected event. Let's call it that. We don't know what
Yeah.
it's going to be.
If your pump is on and filling a tank and you can't shut it off, boom.
Right.
Right. And that's
Exactly.
exactly.
Exactly. Exactly.
Yep. Yep. The next slide.
Okay.
So this was one attack we did on a singular PLC that was at a an antifreeze factory, and a single PLC that was obviously doing something important. We cut network access to it, just like we just discussed, and it resulted in the whole factory and 10,000 gallons burning down. So this
Good
was
job.
one example. Thanks.
Good job.
It was we didn't expect that, right? And this is the randomness of it. We'd attacked this single IRZ PLC the same day we did the 120 telephonist ones, and we saw no impact from the telephonist ones. We don't know what it was because it didn't make the press, but this one IRZ did this great thing in Kindred. Next slide.
Okay.
So now, the last one you also spoke of was electrical SCADA. We've broken into a lot of SCADA systems that are used for controlling power. In this case, there was a battery monitoring system for a huge roadway and tunnel system. We broke into it. You can go to the next slide. It had 249 different PLCs attached to it and a huge battery bank. And as you can see, this case, we I think we caused a fire, but we could never prove it, or we damaged the batteries. But this thing had 120 batteries in it. It was a huge battery backup system. And when we undervolted it, if you can go to the next slide, you can destroy these things simply by, if you get enough access, you can come in and set the battery voltage from 12 volts down to 2, right? And you can set the amps from 5 up to 100. So suddenly you've completely changed the electrical parameters of how this stuff is supposed to work, probably burning out every PLC on the network and or creating fire. And the batteries don't like being put into this kind of a state. Now, of course, we never saw news of this, but the cost would have been huge. Absolutely huge.
We got a question here that's kind of important. It says, user said, I see the PLCs are non-routable IPs, so you're severing communication to the server, not the PLC itself. We'll get into that in a little bit later, user, but notice that the system has a routable IP, but
Yes.
internally they use either non-routable IPs, private IPs, or they actually use, what we'll see later on, is that they use these unit IDs, which are different. Okay.
Yep. Yep. Next slide. They most often use an RS-485 protocol, the serial protocol. So, big SCADA. Let's go beyond the PLC now. Things we've done. When you get to big SCADA like this is a new one. This is the an operation that we couldn't succeed in breaking. So I just use it as an example. But it's you can see in a typical SCADA system, in a big scale, you've got a lot of different moving parts. You've got valves, you've got monitoring systems, you've got control. So it's all usually presented on a screen like this. It has to be constructed, by somebody, a software shop, to represent the live state of a system. In this case, it's a steam water pump system to create steam and energy, and it was running fine. You can go to the next one. I'm just showing you different examples of things that we've seen in Orkland.
I just got a couple of questions here. OptFX says, would you say the typical Western systems are as easily vulnerable? I would say my experiences is that the Western systems are more vulnerable. What I saw take place is that Russia really improved their security in recent years. So when I was testing them long before the war took place, I go out and just test systems, right, to see
Right.
how easily I can get into them. And I noticed that the Russians, maybe about 3 or 4 years ago, and I was going to publish this about 3 or 4 years ago, but I said nobody really cares. I'm not going to publish it. But the Russians really improved their security in their SCADA systems about 3 years ago.
Hmm.
But there's a lot of Western systems that you can just literally walk right into. Okay.
Wow. I don't have that experience. I'm glad you know that because it's
That's
wow.
fascinating.
Yeah.
Next
Go to the next
slide.
slide. Yep.
Okay.
So when you're now the most recent changes, and just to add on to exactly what you said, the Russians have improved their security, but they've also done it by upgrading their SCADA. They used to use a lot of older systems like Rapid SCADA and the like. Now Open SCADA is becoming a much more widely used platform in Russia, um, and we've actually had more success with these than with the older ones because the newer ones are all on the internet. Their PLCs are typically using on a backnet, a private network, and these are totally configurable. You know, they don't come built done. You know, they come as a sandbox, and the company uses consultants to build it. And as you can see in this screen, you know, there's four different on the top. There's four different kinds of views. Some of them are for configuring the SCADA system. Some of them are for using it. And this was the gas complex that we attacked, where you know someone who had broken into the SCADA system before us, okay, which is another aspect of this war that so many people are hacking that you end up running over each other. This someone had
Exactly.
this someone had hacked into this system and was doing something with it. I don't know. Maybe they were collecting data, or maybe they didn't know what to do. You know, it seemed to me like they didn't quite know exactly what to do. They were trying to work the PLCs through the system in a way that wasn't going to happen. Um, but we finished it. Next slide.
I want to just reemphasize what you said. In my hacking, I'm often find myself working against other hackers, right?
Yes.
So you're both fighting for control over a system, right?
The latest greatest loss of my life was because of that.
So
Yes.
you take over a system and then come back tomorrow and somebody else has taken it over, and then you got to go
Right.
back and fight to get control of it again. So
Because it's the same vulnerabilities that everybody can use.
right,
Next slide.
exactly. Mm.
So this is an example of just a quick example of a panel in a furniture factory that we attacked, where you know the operators will have a panel like this. It's a simple red green lights to see if things are working the right way, so that they can scream if there's an alarm. Um, you know, and most data systems are like this, where they have these panels for the knock operators. They're most oftentimes not usable in a way where you can manipulate the system. You can't use this panel to turn machines on and off. You can with the open SCADA systems, but with some of the other ones you can't. Next slide.
Okay.
Do a lot. And this is a quick example of when you do get into an open SCADA system. You know, this was the gas plant attack. You know, you have to know what you're doing because the first thing you see is not quite obvious, right? You don't exactly know where to go with it. And so there's an order of things that you have to do. There's tradecraft. Obviously, changing the language to English is something that I would do. But as you can see, that OTW has mentioned the SQLite database, right? As he said, the database is the heart of a SCADA system, and it's where all the maps are drawn and where all
You
the
can
data
see
is
it,
collected.
see it right here. Yep.
Yep. If you scroll
Also
down,
notice
oh, go
these are
ahead.
all Linux systems too. Right? So these are
All of them.
Linux. Yep. This is these are all Linux systems using SQLite databases.
Yep. Yep. The open SCADA systems are a lot like this. Next slide. I go into more depth about this. So, you know, when you get in, the SCADA system has a number of different subsystems. This is where it gets complicated. You know, you not only the database, but you've got safety, which handles accounts. You've got transports and transport protocols, which talk to the PLCs, and the actual protocols that are used to talk to the PLCs, and data collection, obviously, for taking in data, archives for storing it, and special functions. Module management is where you load custom modules, as you mentioned earlier, OTW. The newer systems, you know, you can have a SCADA controlling a SCADA, and the module management allows Open SCADA to control other smaller SCADA systems, which control PLCs. Next slide.
Okay. Mm.
You know, this is another example of, you know, when you look in the database itself, right on the left side, you have a lot of different tables. And so when you get into it, this is once you're broken in, the hard work begins where you've got to literally go through and understand how their database is set up, what the table structure is, and you've got to go on the right and look at each of the individual tables to understand what parameters are being set, when and why. And it's a lot of information. It is not something you can do in a day or even a week. You've got to really sit down and determine to understand how the factory works.
You mean you can't hack them in 30 seconds or less?
Nope. There's only one thing you can do in 30 seconds or less, and I'll show you that. Next slide.
Okay.
And it's the random
I
kill.
just want to emphasize to people that
Yeah,
hacking is hard work, right?
it is.
It's not this, point a script at a system and then take control of it, right?
Yeah. It's 99% hard work and 1% fun at the end.
Yep.
Yep. Yeah. So, on here, one of the first things that we did in the SCADA system, obviously, is to add our own accounts. And there are ways in which you can add your own account safely. We obviously rebranded all the users with a one fist logo to troll them, and 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 we created our own account, and then under that account, we disabled every other account's ability to modify security. So no other account, including root, could change accounts. And in this way,
Nice.
we gained control. Next slide. Yeah, you can do some fun trolling with that stuff. Here is another example of how complicated the database can be. In the gas plant, each one of these ins are inputs. Then there are variable tables, and as you drill down, it took a long time to finally figure out, oh, this is where the motor speed is for a pump that we want to keep on, not let it turn off. And it's these values that you have to change and know how to do that. And in our case, one of the simplest ways to do it was to change off to on. Right? So anytime anyone hit a button to turn something off, it actually turned it back on. So you could never turn anything off.
Notice is a PostgreSQL database here in this case. Yep.
Yep. And that's actually the most common with OpenSCADA. Next page. I put 40 slides. That's why I'm not going slow.
Okay.
In the subsystems, when you get down to the subsystems, when you're looking at your transport layer, your PLCs that sit off the SCADA system on a backnet usually, there are three different ways that you can access them. One is through sockets, which is kind of a custom way where you can do TCP/IP or you can do UDP or other things. It's usually a custom protocol. You can do serial interface, which is the most common, which is, as OTW discussed, it's most commonly an RS-485 serial protocol.
We'll talk about that next. Yeah.
Yep. And then SSL, which is a secure way of doing, which no one in Russia has done yet. So they have a capability to secure these things, but they don't. Next slide. All right. And so here's an example of looking at the OpenSCADA protocol where you can see some of the PLCs off of that, which are, they have private net IPs, so they're protected behind the SCADA system itself, usually meaning you can't access them on the open internet. In the gas plant case, we could not. They were on TCP/IP, but we could never talk to them directly. So you've got to find those IPs and understand which does which. And you can see on the left, there's different protocols. Go ahead.
OpenFXX, is it more common than RS-232? You don't see RS-232 in SCADA systems for a number of reasons. They're using RS-485 is more common, right?
Yep.
And
that's a
yeah, RS-232 just doesn't work in these kinds of environments. Nick points out, who's done some work in SCADA systems, says RS-485 is extremely common in many building systems as well. That's correct.
Yeah. Next slide. Yep, that's right. We see that too in Russia. So again, and these are the boring slides. We'll get to the fun stuff in a minute. But this is just more examples of the providing of the complexity of things you have to do, like the DAQ logic levels on top, setting parameters the way you want to, schedules. Right now, one thing I should step back and say is that when you build a SCADA system as a factory owner, you get an open sandbox with nothing in it. And you have to build it, literally build your factory inside the SCADA system as a kind of a program or a script, or you can think of it as a sheet of music almost, where you have this program that drives every machine in the factory and the timing and everything else. Okay, and you can have more than one of those programs. So you've got one that was built running the factory, and the way we attack these things is we go in and build another program, and copying the first one and then modify the parameters of it And at the right time, in the right place, we turn off one program and turn on another, and that will start to run our program in the factory, hopefully breaking things. So in open SCADA, everything's done as kind of like a project. That's the right way to say it, a project.
Yeah.
So program. Next screen.
Next slide. Yep.
Yep. And again, you can see the drop downs of all the different kinds of machines that we had at this. This was, I think, at the paper factory. Gas drying chambers, pumps. To your earlier comment, when you shut these things off randomly, you can get lucky if a pump is, gets locked on that's supposed to turn off, and sometimes you don't get lucky. But in the case of a complex attack, you take the time to make sure that everything does exactly what you want it to in the right order, and that takes months.
Yep.
Next screen.
Yeah, it's not a simple attack.
No, you got to know what you're doing. So this is an example of a power station SCADA system that we got into in central Russia. It's called OrkNet, part of the OrkNet project that I just released the information on. And this is an example of a non-live SCADA screen. Older version, it's Rapid SCADA, right? So it's an older model of software, but commercial off the shelf. A company sells this and supports it. And you can literally see the red meaning on and green meaning off lights. Next screen.
Yeah.
And then when you drill into those substations, literally this SCADA system then is showing us the entire power grid. This is you can think of this as a high transmission power line running across the city with multiple drop points to substations along the way. And so once you're inside the SCADA system and have full access, you can modify these things. You can shut off substations, turn on substations. You can see the green boxes on the far right and left. That's the input to the entire string. So you can create huge fires if power plants are constructed only to flow one way, where one side's off and the other side's on, by forcing the other side on, and you get a giant short circuit. But this was an example of one where we had to consult with a Ukrainian high energy lineman. This was to understand what was here in the values. So we couldn't even figure out what this screen did or said until we got a high energy man to get on the phone and say, oh yeah, that's a 10 kilovolt system. It's providing power for 100,000 homes. Like, wow, there's only 4,000 people in this town. So the things that you could never know, often either without Russian translation or truly understanding the nature of the factory that you're in.
I found that most of the systems that come off the shelf allow you to toggle between English and Russian. Is that what you found as well?
Yes, I found that too. Yep.
Yeah.
Next screen.
Good.
Yep, exactly. So this was the power station that we were into, Russia's largest solar power plant, sitting in this remote town. The town is up and to the right of there, and there's huge industrial mines all around this area. So what we suspect is that OrkNet is a giant crypto factory, but it's talking to 54,000 nodes around the world, and we don't know why yet. But anyway, next slide. And that was just an example of how big these places are. And wait, 1 second. To your point, OTW, I want to make one last comment. You mentioned earlier how SCADA systems are truly spread out and dispersed over wide areas. This is a perfect screenshot for that, right? You got to have control monitors, voltage monitors in every panel section of this plant, which are obviously miles from town. So, it's a very sophisticated set of wiring that you have to do just to get that kind of monitoring and control back to the SCADA systems, especially for big places like this.
And every one of those systems is a vulnerability.
Yes. Next slide. So this is an example of, another SCADA view. Some of these have I'm sorry, I didn't have time to unbrand them from I took slides out of our previous work. So just to kind of ignore the text unless it makes sense. But this is an example of an active monitoring system where you could control too. You've got buttons along the bottom where you can turn on and off different boilers, which control different aspects of this particular plant. And along the right, you can see all the different locations that were a part of this particular attack. Next one, next slide. And this is, again, another example of the paper plant that we attacked. We took quite a lot of time to figure out, okay, we want to turn both of those generators in the lower left on at the same time. We want to turn off the transfer switch so that both voltages flow together to create a fire. We wanted to make sure that these big tanks in the upper side are turned on. The valves are left open but not closed, and that all the pumps are on so that they'll fill up and explode if possible. So these are things that we think of when we're attacking, that Americans and Westerners and any friendly power that is protecting their SCADA systems has to consider that once you're inside a SCADA system, it is over.
Yeah.
It's just over. You lose everything after that. Next slide.
Okay.
So this is a slide showing an example of the complexity of the paper mill and some of the stuff that we had to study, taking weeks. Okay, how does a paper factory really work? Oh, this machine's connected. This machine, oh, that's the felt dryer. Okay, I want to turn that felt dryer on at double speed. I want to turn the bottom felt on at half speed, which is what we did to try to create a giant paper jam inside this machine. But it's literally that kind of research that you have to do to figure out, okay, these are the things I need to affect. Then you have to find them inside the SCADA system, however they're labeled. Then you have to figure out how to modify them the way you want. So again,
Let me emphasize, it took you weeks. Okay, that's
many weeks. Yeah,
that's kind of my emphasis here, is that because so many people who are new to our industry don't recognize how much hard work goes in to doing a project like this.
Yeah, absolutely. It's totally consuming. Next slide. I mean, it really is. And the gas plant attack was probably the biggest one. Do the next slide. Yeah. Skip this one. Actually, that's a duplicate.
Skip this one. Okay.
Yeah, okay, let's get to the gas plant. This was the biggest one that we actually completed. Manzaic, I can't pronounce the city set, but it's the largest oil producing city, or was in Soviet times, and is still a huge oil hub. We had control of the entire natural gas plant for the city. It included a backup SCADA system at the airport that we didn't know about at first. So, sometimes, rare instances, but when they're this important, you will actually have a backup SCADA system sitting somewhere else that can take over control if the first site fails. As you can imagine, a system like this, you've got fire, you've got literally this SCADA system controls the fire and boilers. You can turn that on and off and create giant explosions if you had enough control. And the little green dots, above those boilers, that's where you just click and turn things on and off. The big dots in the water pipes in the middle, click, you can turn them on or off. And then at the bottom, you see the alarms. And that's something that you mentioned earlier, OTW, is that these systems are actively monitored by people. So whenever you start to break something, it's going to be known right away, and they are going to react. So you have to be prepared in advance, right? When you launch your attack, you have to have it all planned and done so that when you launch your program, they're locked out and there's nothing literally they can do but scream. And that's it. Next slide.
I think we just lost you there.
Oh, next slide.
Voltage.
Am I back?
We lost the audio.
Okay, I can hear you. Am I back?
Okay. Yeah, you're back now. You're back now.
So again, this is another example of the airport, right? So we got into a real-time battle in this project because we'd spent so long building it, and we launched it. We deleted their program, their project, launched our project, which was very specifically designed. And as soon as things started going crazy, they started getting better again after a bit. Couldn't understand why they were fluctuating. It's because there was a backup SCADA system that Ivan was logged into, running the regular program. So we had to find that. We had to break into it and then delete his program in the backup too, which ended up being a half of a day fight, but we got it. But that's why part of the impact of the attack was not as high as we wanted, because we were literally fighting someone, usually within the same SCADA system, and that is very common, which is why the planning is everything. Next slide. Your pipelines, right? This city had different pipelines. So we were, one of the goals was just a thought was that we didn't do was these three pipelines were originally I was going to turn them full open so that 21 pounds or 26 or 28 pounds on the left would rise to the right. But then we did our attribution and realized that these three lines led to all the houses. And this is where the ethnical aspect of cyber war comes into play, because we chose not to do that. We chose not to attack the hospital or the water supply. We made sure those PLCs were actually cut off at the beginning of the attack from the SCADA system so that they would not be, wherever they were, it was still a random possible effect, but it was much safer than altering gas supplies for residential or city. And that's something that basically dictates the difference between a terrorist and a hacker, in my mind.
Okay. Next slide. Okay.
Yep, keep going. I'm sorry.
What is this one here? Detroit. What is that?
Yeah, there's a city there called Detroit. I was shocked too. I was shocked too. And then the 40 megawatt power plant. Yep, this is the whole city. Every place, even the cemetery. All the natural gas, and then the boxes on the bottom were the transmission lines.
Yeah. Okay.
Took forever to figure it out. And then the SCADA plant system, they'll have views like this. A lot of it's about monitoring and telemetry so that they can see the ebbs and flows of their natural gas pipes and manage their systems accordingly. Next slide. Okay, so back to the safety side of it. Safety in Open SCADA is where you can change things. As you can see, we deleted all their accounts except for user, which you can't delete. We branded all of them with our logo, created a Swordfish account just for us, which was kind of like a secret root account. And for this system, we have different names for each site we use. And that's how we took control. Once that's done, they can't get in, and the user they could log in is had no privileges but to watch. So next slide. Here's an example of a water plant, right? We came across this, did not attack it. But, at first, one of the guys like, hey, I found SCADA, pull it up. And, this is why attribution is so important, because we could literally turn on and off the water with these buttons on this particular SCADA view. The kind of outcome of that for a city wasn't acceptable in our mind. It wasn't a war impacting strike. So we moved on. We actually changed the root password. We garbled it to something impossible so that no one else could break into it using the easy password that they had there. And we'll talk about hacking and bomb lease later because Russians have a problem with default passwords. Next slide.
I found default passwords in a lot of places besides Russian too.
Oh, is it? Okay.
I find default passwords all over the world.
That's crazy. So that's just another example. You can skip that one.
Okay.
Just providing different screenshots of examples. In this case, we of course always branded the site. The station name became Team 1 is Demolish You. And we went through and we deleted the database. And this is one comment I wanted to make about SCADA systems, especially Open SCADA. You can do the 30-second attack. If you break into a SCADA system, you can go right to the screen, right-click, and permanently delete the database. It's gone, just like that. The whole system will continue to function normally until it needs to reset or draw new parameters in for the next round of manufacturing, and then it will just stop working. But the displays will stop working before then. It's completely random, right? You don't know what you're going to do. You don't have any idea if there's going to be any impact at all, and you might lose the ability to have an impact by simply deleting the database. So it's not a good idea if you go through the trouble of getting into one to be that reckless. Yes, it takes a long time to develop a right attack, but the result is far better.
Notice the transport protocols over here. You see that they're using Modbus, OPC UA, which we're going to be talking about each of these in a little while. HTTP, some proprietary open SCADA, and custom.
And I've seen examples of all of those used. So it's good that you're going to talk about them. Yeah. Next slide. It's good. We've seen them all used. Did you lose me? Am I there? Okay. Yeah. Next slide. Cool. Are you there, OTW? Oh, I see. OTW's audio went out again.
Oh, okay.
We'll come back.
Okay, here we are. We're back.
Next slide. We didn't miss anything. Okay. And thank you for doing this, sir. Really
Of course. Thank you for coming on here and doing this.
You have done so much for us, sir. I owe you, and a lot more than this. So we are very grateful for you. But this is a picture of the actual paper machine that we destroyed, and I'm hoping that there was a giant paper jam between these two big rollers that would really screw those machines up. Next page.
Okay.
So now we get down to the last bit of the discussions, packet analysis. I don't go too far into this other than to say that Wireshark, if you can get TCP dumps in a network for SCADA, you can really gain control fast. You can get passwords. You can understand what's happening. And Wireshark is something that we had to use in our last project to understand anything. And it helped a lot. I'm not going to go into any more detail about it other than to say that, you're going to train on it and it's a very important subject.
Yeah, we'll be working with some PCAPs in analyzing some SCADA traffic.
Cool. I have my PCAPs from OrcNet too that I'm happy to share for the class.
Oh, great.
It's got 3 SCADA systems talking through it, so I figured it might be a a good one. Again, this is just some more examples of packets and the kind of data that you're going to see and the analysis that we tried to do to understand what was happening on a SCADA network. And it was a mixture of SCADA packets and this mysterious protocol. So you'll find lots of things and interesting things when you study Wireshark PCAPs. Next slide.
Yeah.
I think it's the last one. Yep. And then we just trolled them. But the point of this slide is a PCAP can give you all the credentials you need. As you can see down in the lower left corner, finding the
Right
right pack PCAP. Yep. It gave us the credentials for logging into this super secret network for at least one user. We gathered all the information. We captured about 9 or 10 of those. And we still have them. We released with the batch of data, we released those accounts.
It's important to note here that they're transferring username and passwords in clear text, right?
Yes.
And that's not unusual. So keep that in mind.
That's right. When you're seeing at the packet layer, you can see a lot more than you normally can. It's very, very powerful. Next screen. I think that's it. Is that the last one?
Somebody pointed out, Control pointed out, that's date of birth. So it's September, or actually June 9th, 1972. So we know a lot about this guy.
Yeah. But see, that's the thing, right? I did not know enough about Microsoft SQL database or this protocol to diagnose it before the Chinese came in and took it away. Well, they didn't take it away, but they attacked it and made the orcs aware of it, and the orcs fixed it. But
Right.
it's but I hope to learn. And it's an example of.
When you say orcs, you're referencing the Russians.
Yes.
Okay.
Yeah, I usually call them by orcs now,
Right.
and I never capitalize Russia. It's just something that we do on the team. I'm sorry, I should have been more clear about that.
Well, I'm familiar with that terminology, but not everybody maybe. That's why I wanted you to clarify it.
Yeah, it's a common thing in Ukraine that we refer to Russians as orcs because they are no better than that, and et cetera, et cetera.
Okay.
Yep, but that's my presentation on what we've done. We've probably destroyed a dozen large SCADA systems so far, and probably 400 or 500 PLCs in Russia. The alone ones. And looking for more. I've got 3 SCADA systems that I want to break into that I haven't broken into yet. So I'm still hoping to learn, from you in the next day, sir, about how to do advanced SCADA. I'm very excited and very grateful for everything that you've taught us.
Thanks, Voltage. I appreciate you coming in and doing this. I think everybody else appreciates what you're doing and this presentation. So thank you very much. Let's go ahead and take a little break, you guys, and we'll come back and do some more on the protocols. So let's come back at like 13 minutes after the hour, and let's all give a big thank you to Voltage and Team One Fist for the work they're doing to help protect Ukraine. Thank you, Voltage.
Thank you, sir. Appreciate that.
This conference will now be recorded.
Okay, we're back. And before we move on, I want to thank Voltage once again for coming in and doing a presentation. And I want to thank him for all the work that he's doing to help save Ukraine and the whole Team One Fist. So thank you, Voltage. We really appreciate your work. Now, what I want to do next is I want to talk about some of these protocols. When we looked at Voltage's presentation, we noticed there was various protocols there. One of the things that I mentioned early on is that one of the key differences between SCADA systems and traditional IT systems is that they're using different protocols and they're using different media. One of the things that came up in the questions, when Voltage was doing his presentation, is that these internal communications are over serial connections, and they use RS-485, and we'll talk about that more in just a moment, okay? They don't use RS-232 because RS-232 has very limited distance, okay? And it also is more susceptible to EMI, electromagnetic interference, which in an industrial capacity, you have a lot of EMI, right? You got a lot of machines, a lot of motors, a lot of generators, and they all create EMI. And so you have to have a media that's resilient to EMI, All right. So any questions before we get started for Voltage or for myself? Okay. All right. Let's move forward then. Okay. So this module, one of our goals is to examine the common ICS protocols with an emphasis on Modbus because Modbus is first and most widely used. Okay. Just lost the audio there. Okay. You're back. Good. So Modbus becomes kind of this universal protocol that allows different PLCs to communicate with each other. Now, that's an option. It isn't always used, right? So the first place in trying to understand how these systems work is to start with Modbus, and that's our goal for this class or for the next couple of days, right? Is to understand Modbus, okay? Now, we're also going to discuss how field protocols are migrating to IP, right? Enumerate some protocol weaknesses and discuss what security should be in a field security protocol. So when we say a field protocol, these are the ones that are being used in these systems, these SCADA, ICS. These are field protocols. That's the terminology that people use. All right. Some of the field bus protocols, there's serial communication. This is usually serial within the facility, right? When they're used to communicate from PLC to the actuators and sensors, it's rarely a cybersecurity concern. A physical attack is easier. It may be a future concern, okay? When used to communicate from the control center or the MTU to a PLC or RTU, there's a minor concern. These are often referred to as serial comms, okay? Hacking tools will generally not work, okay? They're not connected to any other IP networks, okay? So I also want to point out that there's multiple attack vectors in SCADA, all right? And when Voltage was doing his presentation, he was showing you what essentially are the human machine interface. So if you can get into the human machine interface, then you have control over the system. All right. There are at least two different approaches: is getting into the human machine interface or attacking the protocols. Some of the ICS communication protocols, okay, include Modbus, DNP3, which is primarily used in the electrical industry, like electrical distribution industry. There's OLE for process control. We saw that being used in one of the slides that Voltage showed us, where we had multiple protocols, and one of them was Modbus, and one of them was what's called OPC or OLE over process control. Okay. We have Profibus, we have the Foundation Field Bus H1, we have the Intercontrol Center Communication Protocol or ICCP, we have the Common Industry Protocol. This includes Ethernet IP, ComponNet, ControlNet, and DeviceNet. But there are over 200 protocols. This is part of the problem, right? As an attacker, this is one of the problems, okay? Is first to figure out what protocol is being used, right? And then be able to understand how that protocol works. But these protocols tend to be simple protocols. They have to communicate over serial connections. So they're really lightweight and simple protocols. And that is their weakness, right? So let's take a look at some of these. Communication between the control center and the PLC RTU. It was serial, okay, moving almost entirely now to IP, including Modbus, DNP3, Ethernet IP. Now remember, this is the control center, and the PLC RTU. Renegade says, is that what we saw in the Wireshark screenshot was the login information? Yeah, so when you're looking at that screenshot on Wireshark, we'll get into this in a little bit, but that's the communication external, okay, or between different units, right? OptFX says, so once we have a compromised the TCP/IP network, how to gain control and begin moving around? Yeah, so this is more generic. This question is more generic. How do I go ahead and move from a single unit in the business network and move into the SCADA network? And that's something that we do in some of the other classes. Probably not going to do that in this class, right? Here we're going to focus on the SCADA network because that's really the mysterious part for most people. Is how do we function in the SCADA network? Getting from attacking the business network, okay, is something that's pretty well known. Most of us are familiar with that. And being able to pivot from that into the SCADA network is part of a typical hacking penetration test, okay? Yeah, how to pivot from one to the other. The communication between the PLC RTU and the actuator sensor can be DF1, CAN, Modbus. CAN is largely another one of the protocols, and we'll see if you're signed up for the car hacking course in October. CAN is one of those protocols. Once again, it's a serial protocol that's being used in vehicles, cars and trucks and what have you, okay? Modbus, DMP, and others, okay, more likely to stay serial. Most of the protocols, okay, have been able, what they've done is they've converted or encapsulated the protocols, okay? Yeah, so CAN is also in SCADA, exactly, Cyber Mayhem. So they've done is they've gone ahead and encapsulated or converted the serial protocol to be able to communicate over TCP/IP, all right? By doing that, they get higher data rates, okay? The RTUs and the PLCs often have Ethernet cards, okay? The shared WAN LAN, wide area network, local area network, were used for enterprise and SCADA. Deploying 2 WANs is expansive. Routing provides alternate paths for availability. Less custom equipment is necessary, therefore makes it cheaper to operate these facilities. So what we're going to see is that almost everybody uses a TCP/IP on the outside of the facility to communicate to some terminal that's able to control the facility or manage the facility, or they'll use TCP/IP to communicate between different units. Industrial Ethernet, basically serial comms, are encapsulated in TCP/IP packets. That's certainly true with Modbus and DNP3. So Modbus, okay, becomes Modbus TCP. DNP3 becomes DNP3 over TCP/IP. So this is the original serial protocol, this one here, and then they go and encapsulate it into essentially it's like a frame around the packet that allows it to be able to communicate over TCP/IP, because the serial protocol cannot communicate over TCP/IP. DeviceNet becomes Ethernet IP, Profibus becomes Profinet, Foundation Field Bus H1 becomes HSE. These are all the TCP versions of the serial protocol. Let's talk about Modbus first, okay? Modbus is, for our purposes, is the most important, okay? And it's almost like a lingua franca of the serial communications. Almost every PLC will have a Modbus connection, okay? So that if you have multiple manufacturers in the facility, you can choose to have them communicate over Modbus so they all can talk to each other. Modbus was first developed in 1979 by Modicon. It's a common protocol for connecting multiple devices from multiple manufacturers. It's free and open source, okay? The original one was Modbus RTU. It's a compact binary format. We also have Modbus ASCII, was more verbose, but it was human readable. That was what you seldom see it. It's out there, but you'll seldom run into it. Modbus TCP is similar to Modbus RTU, where data is stuffed into a TCP IP packet. We'll get into diagramming these protocol in just a little bit here. The importance of Modbus. It's the most widely used protocol in SCADA systems. Most SCADA devices either use Modbus or have the option to use Modbus, right? And we saw that on some of the slides that Voltage showed us, is that we had multiple protocol options, and Modbus is almost always like 90+ percent of the PLCs will have an option to use Modbus, okay? Often used to connect devices by different manufacturers. The history of Modbus: originally, all valve sensors and actuators are connected back to a central computer, originally. This is very expensive to wire them all back to a central computer. Modicon, okay, the company, develops the PLC. The PLCs could be distributed throughout the plant, reducing cabling costs. So this is kind of like the history of industrial systems. Originally, everything communicated back to a central computer where all the logic was built in, right? Very expensive way to manage a plant, right? So now Modicon develops the PLC, and we can put the brains into the plant, distributed throughout the plant. That's the development that Modicon made that now we all use, right? And they developed Modbus. They still needed a way for the PLCs to communicate with each other, okay? In 1979, Modicon develops the Modbus protocol. Okay, the name comes from Modicon, the company name, plus field bus. These are field bus protocols. So they just combined the two together and they got Modbus. With Modbus, all the PLCs in the plant could share their data over a single cable. It's also important to note, as we get into this, is that Modbus operates pretty much like the old, similar to like they send data like over a broadcast domain. So all the data is sent over across all of the PLCs. Okay. This enabled all the PLCs to share data and control, resulting in a fully functional plant control system. Modicon published Modbus as free and open standard. It's very simple, flexible, and soon many other PLC manufacturers adopted it. Many other manufacturers of PLCs support their own proprietary protocol, but also Modbus, as I mentioned earlier. Okay, so they'll have their own protocol, and literally there's over 200 protocols, but they also support Modbus. All right, this is what goes to OptFX's questions earlier. Early connections of computers use RS-232 or serial ports on PCs. It was a point-to-point standard, one device to another. Those of you who are old enough remember that this was used for your printer way back in the 80s and the 90s, okay? It's effective only up to 50 feet, right? It's not resistant to EMI. Now think about all the EMI that there is in an industrial facility, right? There's huge, far more there is in your home or office. So to use a protocol that isn't resistant to EMI, you're asking for trouble. So what was developed is another serial protocol, serial medium, called RS-485, and it can connect up to 32 devices. It's effective up to 4,000 meters and resistant to EMI. Okay, let's look at how Modbus works. It's a request and response system. PLC A, okay, requests information from PLC B, and PLC B responds with information, okay? So this PLC asks for information, PLC-B responds back, right? Otherwise, there's no communication. It's a request and response. PLC-A, okay, is acting as a Modbus master, and PLC-B is acting as a slave, right? So the PLC that is asking for the information is the master, and these are the slaves. On a Modbus network, there can only be one master. Modbus master makes requests of the slaves. So request slave 1, slave 2, slave 3. We'll see later on that these have what are called unit IDs. They're similar to an IP address, but they're much simpler, right? It's just, this is unit ID 1, unit ID 2. So when master wants to communicate with these PLCs, it sends out a request that includes the unit ID number. Slaves only respond to requests from the master. There's no unsolicited responses. So that means that these slaves will never send information back to the master unless they're asked. They don't speak unless they're spoken to, right? Once configured as a master, always the master. The unit ID uniquely identifies each unit on the network. The unit ID is the address of each device. They range between 0 and 255. That tells you that it is 1 byte, right? 0 to 255 is 8 bits. That's the maximum number that you can represent in 8 bits is 256, right? 0 through 255. Each one of them has to be assigned a Modbus ID, range of 0 to 255. Modbus messaging, the unit ID is set at the programming, okay? It's permanently stored in the Modbus device. When the master sends a message, all devices hear the message, okay? It's similar to a broadcast message or old hub messaging. When before we had switches, we had hubs, and the hubs simply took the message and sent it on to all of the nodes on the network. That's the way Modbus operates, okay? But it's in modern days, this doesn't work really well on Ethernet because you get a lot of congestion. But in Modbus, it works okay because the packets are so small and there's not that much communication. So it doesn't create the kind of congestion that you would see on an Ethernet network. If a master wants to request data from the slave, all receive the request. So when master says, I want some information, okay, and the information, we'll see the information that the way they communicate what information they want is by a set of codes. And so they send out a request, everybody gets the request, but only the slave that's intended to responds, okay? The master embeds the unit ID of the slave it's requesting data from in the message. Each unit receives message, but only responds if the ID matches its internal ID, okay? So it sends out, here's master, it sends out a request with the unit ID of 22. It goes to the first slave, who's 21, and there's no response. It goes out to slave 2, which is unit ID 22. It responds. So all of the PLCs get the message, but only those who it's intended to respond. All receive the message, but only unit 22 will respond. This would not work, obviously, on an Ethernet. I mean, it used to, in the early days of Ethernet, this is what happened. But obviously now it would create way too much congestion. But these systems, there's not that much communication and the data is very small. We'll see that when we start analyzing the packets. Many types of request commands, depending upon what the master is trying to do. Okay, and these are all assigned a code, so you can read the coil status. Now, if you're not familiar with this industry, way before it was digitized, everything was an electromagnetic switch, and that's where the term coil comes from. Okay, but you'll see that term used in the industry as a coil. So as you can imagine, an electromagnetic switch is either open or closed, right? It's either open or closed. So it means it's only 0 or 1. So coil statuses are only going to be, they're going to be a binary field. It's either going to be 0 or 1, right? But there are other memory areas, okay, that can have, depending upon the protocol, a byte or 2 bytes of information in them, all right? So we can read the input status on them. We can read the holding registers. We can read the input registers. We can force a single coil. We can preset a single register, and we'll look at each of these. The first 4 of those involve the master requesting data values from the slave. The master must send the unit ID, the request type, and what memory block it wants to read. Now that's important here. It has to tell it what memory block it wants to read. The last 2 commands are write commands, force a single coil, or preset a single register. Okay, these are writing to the PLC. For example, what if master wanted to read the 2 memory blocks, 10050 and 10057 from slave 1, unit ID 21, okay? Here's unit ID 21. So it goes read the status, input status, Modbus unit ID is 21, block address is 10050, 10057. It comes to slave number 1, all right? It says, I want to read the data on this memory block. Modbus can only request contiguous memory block addresses, okay? Once again, very simple, all right? That's what keeps the protocol very simple and lightweight. Master's only interested in 10050 and 10057, but it has to go ahead and read all of those, all right? And then it'll parse it out when it comes back to the master. The read request must indicate a starting memory block and the number of blocks to read, okay? So it comes in and says, I'm gonna start at 10050 and I wanna read 8 blocks, right? It's gonna get everything in between as well. And then it has to parse it when it gets back to the master. The slave will send 8 blocks of data. The master will extract the data it needs from 10050 and 10057. It ignores all the other data. It's inefficient, obviously, but small amounts of data. So therefore, it can live with this kind of inefficiency because it's really very, very small amounts of data. We're talking about 1 byte at a time. In some cases, 2 bytes at a time, very small amounts of data. Okay, so Modbus and some of the function codes, all right? So we're talking about some of the requests that the master might make. So the function code 01 is the read the coils, okay? Remember, the coils are on-off switches, so they're always 01. Read the discrete inputs, read the holding register, read the input register, okay? Number 5 is write a single coil. So these are more malicious, obviously. These are going to be just reading the data. And in all honesty, on a lot of systems, probably half the systems that are connected to the internet, you can read the data from the PLCs. Writing is a different subject. Sometimes writing can be, you can get in and actually write data to the PLC. Imagine that. I'm sitting wherever I'm sitting on the internet, and I can write data to the PLC. So I can write a single coil, write a single register, write an exception status, or number 8 is diagnostic, right? So diagnostic is where the system is checking on the status of a PLC, and we'll see that one of the diagnostic codes can basically be used as a DOS attack against these systems. Here's the Modbus TCP. So we'll see here is that here's the transaction ID, the protocol ID, the link, the unit ID, the function code, and the data. So the original Modbus only included this part right here, right? And then they added on to be able to send it over TCP/IP, length, protocol ID, and transaction ID. The protocol ID is always Modbus, okay? I'm sorry, it was always TCP. They originally designed it so it might be able to be used over other protocols, but that's never happened. Okay, it's widely used across various industries. Many protocols are industry specific in practical use, but not in function, right? So like for instance, DMP3. You won't see DMP3 used anyplace else but the electrical industry, right? So, but Modbus is used across industry lines. There's a lot of variance and customization, okay? So we talked about the fact that Modbus is open source, right? But the company can go ahead and put in their own modifications to Modbus. So like Schneider Electric has what they call like Modbus Plus, which is Modbus plus their proprietary fields that are in it. So for instance, they can add report by exception, add new function codes, they can support longer length messages. These are all things that they can change about Modbus in their own proprietary specifications. Modbus is a serial protocol. I mentioned request and response. There's no report by exception. Okay, some of the function codes we already talked about. Notice that the data is maximum 253. And here's a more complete list of the Modbus functions. These are the hex code. These are the codes in hex. Okay, read coil, read input, read holding registers, read input registers, force single, preset single registered, read exception status. Okay, and then we got a few more over here. This does not include, this is not showing us function code 8, which is the diagnostics code. We'll get to that in a minute. So these are diagnostic codes. Okay. Return query data, restart communication. The key here, the one you want to pay attention to, is force listen only mode. Okay, this is a common DOS attack against Modbus systems. If I can send in codes into a Modbus system, okay, I can go ahead and put it into force listen only mode so it doesn't respond to the master. It listens only. And this has been used in the past on various DOS attacks against SCADA systems. Here's a little more on some of the protocol versions. We have Modbus TCP, which is the one that's most often used, okay? Removes the checksums in TCP. We have Modbus over TCP. We have Modbus Plus. This is the one that Schneider Electric uses on their systems. And they all use port 502. So if you go out and start scanning systems looking for port 502, in most cases, probably over 80 to 90% of the cases, if port 502 is open, it's a Modbus system. Now, I've seen a lot of systems that use port 502 for other communication, but in almost every case, 502, like I said, 80 to 90%, it's going to be a Modbus system. So that makes it pretty easy to find, right? You can go to Shodan, you could use Nmap, what have you, try to find port 502 open, and you've probably found a Modbus system in most cases. Here's the Modbus packet. Okay, here's the original packet. Right, this is the Modbus RTU. This is the one that's being sent over a serial communication. We have a slave ID, the function code we just talked about. Whatever data is in there, sometimes this is going to be either 1 byte or 2 bytes, so it's pretty small. And then error checking here. All right. Then to get it to move over TCP/IP, they add a few more items here. Notice that they now have a transaction ID, a protocol ID, which is always TCP, the length, and the unit ID. And then it still includes the function code in the data. Modbus application protocol, this was often referred to as MBAP. Like if you're using Wireshark, you want to select MBAP for the protocol. It's 7 bytes, 2 bytes of a header, 2 bytes of protocol ID, 2 bytes for length, and 1 byte for address. Seven bytes total, pretty small. Modbus RTU uses serial, binary representation of data. It uses CRC for error checking. It's framed, separated by idle periods. So this is important, okay? So there is no way to separate the frames except for there's a time gap between them. Instead of binary, it uses ASCII characters. It uses longitudinal redundancy check. It's framed by a leading colon and a trailing new line. Sorry, I just get more people sending me emails that trying to get in the class. Okay, there's no security, there's no authentication, there's no encryption. Okay, pretty serious stuff. Here's a Modbus DOS attack. Okay, so this is what I was talking about here. Is this is using the function code 8. Okay, subcode. So there's codes and then subcodes, right? And this is subcode 4. It's function code 8, subcode 4. 4 is listed. This is actually from a PCAP that we'll use in class tomorrow, and showing us that somebody's trying to do a DOS attack against Modbus here. We're going to leave the simulation till tomorrow. All right, I'm going to go through these protocols, and then we'll leave our analysis and simulations till tomorrow. Okay. Let's talk about DNP. All right. So I promised to get you out of here in 4 hours, so we're going to just cruise through some of these here, and then we'll leave tomorrow, lab time for tomorrow. So DNP is largely used in the the electrical distribution industry. Okay, it was originally developed by Westronic. It's now GE Harris. Developed in 1993, so a little more modern protocol. It's based on an early draft of IEC 60870-5. So these are kind of like requests for comments. These are developed by the industry, the experts in the industry, and they used IEC 60870 as a framework for developing DNP3. It's community managed, dnp.org, used primarily in electric and wastewater, water and wastewater industries. It's highly tolerant of EMI, as you would imagine, okay, because it has to be able to work on a really strong electromagnetic field. It tolerates EMI, and it also tolerates poor transmission media. It's client server. It's encapsulated in TCP/IP. It does support unsolicited response. Its default port is 2000. Frequently used in the electrical industry. It could be used in others, but it's not. Similar to Modbus in many ways. It's originally a serial protocol. Now there's an IP version. It uses a client server. Okay. The server is the field device. It does have some differences, and that is it report by exception. SCADA server polls for change events. That should be polls, not pools. So the SCADA server is polling. It's going out and asking the slaves, is anything changed? Is anything changed? Is anything changed? Is anything changed? And so it's asking to see if anything has made any changes. And the slave can go ahead and report back without being even polled. DNP3 is unsolicited response. Slave sends updates without polling. Okay, this is a key difference between Modbus. Modbus will not do this. James asks, we use the same meeting invite code for the whole week. That's my intention, James, but I will send out every day an invite code. But sometimes I found the GoToMeeting will change the code. So that's why you still got to watch for it. But I'm intending to keep the same code every week if I can. All right. It's defined by other layers, such as applications, transport, and data link layers. Yeah, that'll make it easy to come into class tomorrow. So the DNP3 has a control byte, a transport layer byte, an application layer control byte, and data chunking. So it has a 2 CRC byte every 16 bytes of data. Here's the function codes in DNP3. We have an internal indication flags in DNP3. So this the bit 0 would be last received message was broadcast. 1 would be class 1 data available. 2 is class 2 data available. So the IN flags are set by the slave station to indicate internal states and diagnostic results. IIN set as a 16-bit word divided into 2 octets of 8 bits. See it, DNP3 environment. There's no security in DNP3 either. Now DNP3 is a simple attack, once again, similar to what we had in Modbus. So in this case, in DNP3, the function code 21, okay, disable unsolicited messages can be used as an attack. The slaves will not communicate back to the master without polling. This would be function code 21. So if I can send function code 21 into the PLCs, right, then they will not respond to the master. So to do this attack, the intruder initiates a connection with the slave, posing as master 6. Now there's no authentication in these systems, so it's easy to spoof. The intruder sends a message to slave unit, say 245 with a function code 21. Slave unit 245 receives the message and disables unsolicited messages function. At this point, the slave will not be able to send any alarming messages to master in case there's a failure or abnormal operation of the slave unit. The intruder sends another message with function code 18 to slave 245. Code 18 gives instructions to the slaves to stop running the application specified in the message, and there's no way that the master is going to know this, right? Essentially, we're talking about a DOS attack here. Or, if we're talking about just stop running the instructions, right? Who knows what the effects are going to be in a system like, say, a chemical plant or a refinery. A simultaneous attack on another slave units will disable all operations on the communication channel. DNP3 has the capability of sending a broadcast message to all the slaves by using the address 65535, right? That's the largest number represented by 16 bits. This could interrupt the utility service of that region, like shutting down the electricity services. At this stage, the master terminal unit in the master station reports the application is running normally. Nothing will be known, while the remote terminal unit in the slave station receives tampered frames. The original DNP was an application level security, okay, based upon IEC 62351-1. It had a shared secret key, so like a password. Had to be manually applied, had no key management standard, it's not widely used. DNP Sect v5 is based upon IEC 62351-2. The security threats that it addresses, including spoofing, modification. Now, notice here that in Modbus, there was no way to know whether or not, one, we're coming from somewhere on the outside or somebody even on the inside sending messages to the PLCs. So it's easily spoofed, okay? If I can intercept the messages, I can change them, okay? I can go ahead and capture messages, communication, and replay it, but DNP Sec 5 is trying to address those weaknesses. It also tries to keep from eavesdropping on key exchange. It's still in definition, Okay, versions 1 through 4 have been dropped as ineffective. DMP3 still really has no effective security. OLE for process control was developed in 1996. It's based upon Microsoft. Okay, this becomes OLE, OPC. We saw that in the presentation that Voltage gave us. We saw that was one of the options, and we'll see that OPC is used oftentimes to translate the various protocols so they can talk to each other. Right? That's what OLE is largely used for. It uses object linking and embedding from Microsoft. It uses component object model, the COM model, distributed component object model, DCOM. These are all Microsoft technologies, as we all know. The most common specification is OPC data access. One of the things that's important about OPC is that many of the Microsoft vulnerabilities are built into OPC. So if the system is using OPC, not just has the capability of using it, but is actually using it, many of the attacks against Microsoft products will work against the SCADA system, right? So if they're using OPC, so this is, once again, renamed. It was originally OLE for process control. Now it's renamed the Open Platform Communication, commonly used to communicate with databases and ERP systems. One of the things it's also used for is that one of the problems that you have with SCADA systems is that a lot of the security systems, like the IDSs, like firewalls, won't work internally on these protocols, right? And so one of the things that a lot of the SCADA systems use for security is they'll use Splunk, okay? But Splunk doesn't recognize SCADA protocols. So what you do in that case is you put in an OPC server between your Splunk machine and your SCADA network and let OPC communicate with the SCADA, translate it for your Splunk, and then Splunk can be used in terms of trying to monitor the system. It's commonly used in databases and ERP systems, increasingly used to communicate with PLCs via a gateway device, exactly what I'm talking about here. The classic was based upon Microsoft DCOM as the unified architecture based upon web services, XML, SOAP, and .NET. Open platform communication. Basically, what I'm trying to say here is that the vulnerabilities that we know are built into Windows operating systems are then transferred into the SCADA systems using OPC, making it relatively or easier to be able to attack these systems if they're using OPC. Like in Voltage's presentation, we could see that it was using multiple protocols, excuse me, multiple protocols, and OPC was one of them. Now, just because it's capable of OPC doesn't mean it's using OPC, okay? Cal says, how often they're using OPC? In a relatively small number of units, because once again, it's used for communicating with outside systems. Like I said here, is that it's often used to communicate with databases and ERP systems, and it's also used to be able to communicate to anything else that is on the outside, like a database, like I was mentioning, like a Splunk system. You'll find that probably in maybe like 10% of systems. So a couple questions. Control asks, also everything from Microsoft needs to be restarted again regularly to get working again, as we all know. And you mentioned ICS needs to work at all times. Yeah, right. Okay, good. So the vulnerabilities that we find in Microsoft systems are built into OPC systems, making the systems that use OPC more vulnerable than others. OPC security is questionable. Yes. TASE, okay, or ICCP, It's a telecontrol application service element. There's a lot of information I'm giving you here, and this is part of the reason why the industry has largely been immune from cyber attacks, is because very few people know all this information, right? And there's so many protocols, and each one of the protocols has its own fine points, okay, that you need to be able to understand to be able to effectively attack. But this is another one of the protocols, okay? This is by the electrical industry, developed by EPRI and Northern States Power. EPRI is the Electric Power Research Institute. It's a prestigious research institute in the US, in Minnesota, and around Stanford, I think, is where they have offices, and Northern States Power, which is based in Minnesota. They developed this protocol to be able to communicate within the electrical grid. It's widely used in utilities. I'm not going to spend a lot of time on it, okay? It uses port 102, client server model as well. We also have the ICCP transport services. It's ISO transport services on top of TCP. It emulates the ISO transport services, or COTP, on top of TCP. Secure ICTP was developed in '97. SCADA EMS vendors have been working with it since 2003. Many systems have secure ICTP licenses, but very few systems use it. The business process to establish and maintain data flow using secure ICP are not overwhelming. In other words, you don't have to make a lot of changes to be able to use it, okay? Governments or regulators could write laws and regulations requiring it, but of course we know that Nick corrected me, and Northern States Power is now part of Xcel Energy. Thank you. All right. So this is a more secure protocol. We just don't find it being used, okay? Secure ICP assures only authorized access, even within a closed private network. Prevents eavesdropping by non-trusted entities, prevents spoofing, playback, okay? So regulators could dictate and mandate that this protocol be used, but they're reluctant to do so. Uses TLS encryption. I'm just gonna, like I said, I'm gonna go quickly over this, okay? This is a more modern protocol, but unfortunately it's not being used. Security is still questionable, but it's far better than you'll see in the others. Common industry protocol, or is this largely used among manufacturers? It's used for control, safety, synchronization, motion, configuration, and information. It's managed by a community, the ODVA community. There's 4 protocols: Ethernet IP, Component, ControlNet, DeviceNet, okay? Uses, the TCP uses 44818. You can go on the Shodan and find these by just looking for port 40. This is a port that you're not going to find hardly anybody else using, but the CIP folks, and UDP 2222. Whereas port 502, you will find people using it for other purposes. Here's the common industry protocol diagram. And this is going to be the last one I'm going to cover, okay, for this class, and that's Profibus Profinet. This is what Siemens uses. This is what was used in the Stuxnet attack, right? When they were attacking those PLCs, they were communicating over Profibus Profinet. It was developed by Profibus Profinet International EV. It's an open standard for industrial automation. It can be used either serial, which is Profibus, or TCP/IP, which is Profinet, okay? It uses keyword or XML to communicate data. Profinet IO uses TCP UDP ports 34962, 34963, 34964, and then 34964 is connectionless remote procedure call. There's Profinet CBA. There's actually multiple versions of Profibus Profinet, okay? and this communicates over port 135. Here's kind of a comparison of Profibus, Profinet. The old Profibus, you can see, was only 12 megabits per second. Okay. Profinet, the faster and more modern, is 100 megabits. And you can see, okay, you have Profibus networks. There's many, okay. You can see here, Profibus DP runs over RS-485. There's Profibus PA, right? And here we see Profinet up here. I think I'm going to leave it there. Let's just talk about a couple things about ideal protocol, okay? So if I were to create an ideal protocol for SCADA ICS systems, what would I want? I want a source message is authenticated, okay? So right now, most of these protocols, you can actually spoof on them. There's no way of authenticating that you are a legitimate user of this network, okay? I want the contents of the message to be authenticated. I want to be able so that I can't do a man-in-the-middle attack on them. Right? This is what I'd want. This is ideally what I want. Now, you're not going to find this, but this is what ideally we would want. We want encryption for confidentiality. Now, what we're going to see is that because these are serial protocols and they're lightweight, there's no encryption. And on older systems, the chips within the systems are not powerful enough to encrypt and decrypt. So we don't have any encryption going on inside these systems. So if you can get yourself in between and read the communication, you're going to find it's all clear text. And then you want it tuned for performance, okay? After you put all this stuff in it, you want it to be fast, right? And of course, the more you put into a protocol to make it secure, the slower it's going to be, and the more CPU power you're going to need to run it. It doesn't exist yet. There's virtually no security in existing protocols, so we can spoof, we can replay, we can DOS. Those are all possibilities. Close to the ideal, even close to the ideal doesn't exist. And we're just at the stage in the evolution of SCADA where people are beginning to try to put together protocols that will be secure. But unfortunately, okay, we aren't there yet. And legacy systems, you can't implement these in the legacy systems without gutting them, okay, and rebuilding them. So will the vendors, if you put together an ideal protocol, will the vendors support it? Maybe, maybe not. Maybe it requires government mandating that they do. And then there's an issue of legacy equipment. Like, we're talking about systems that some of them are 50, 60 years old, right? It may not be possible to redo them with a secure protocol. So Voltage says, not without paying for them to develop the code and implement it. Yeah. Okay. Let's call it good for today. We're a little bit over. I try to keep it under 4 hours. Tomorrow we'll get a little more technical. We'll spend some more time doing some simulations to get better understanding the Modbus protocol and maybe some ladder logic. We'll do some reconnaissance to find these, show you how to find these systems. Usually these systems are all online and you can find them using various tools. So that's what we'll do tomorrow. Thank you all for coming. Thank Voltage for his presentation. And we'll see you tomorrow, same time, same place. And hopefully the ID will be the same. If it's, whether the ID is the same or not, I will still send out the mass email to give you a meeting ID, but it should be the same tomorrow. Thanks for coming. See you tomorrow. Bye-bye.